Welcome back. Tonight, we settle in with the patient, painstaking work of astronomers who, night after night, photographed faint smudges of light in the cold dark of mountain observatories, measuring the subtle reddening of distant galaxies, comparing photographic plates, calculating distances so vast they seemed almost meaningless, until, gradually, through years of careful observation and quiet disagreement, they came to understand that the universe itself was stretching, carrying everything slowly, silently apart, like dots on the surface of a gently inflating balloon. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the early years of the 20th century, as you settle in and let your breathing slow, the astronomers and physicists of that era held a belief about the universe that had remained largely unchanged for centuries, a belief so deeply embedded in scientific thought that questioning it seemed almost unnecessary, almost beside the point, like questioning whether space itself existed or whether time moved forward rather than backward. This belief, held by nearly everyone who studied the heavens professionally, was that the universe was static, eternal, and fundamentally unchanging in its largest structures, a vast and permanent stage upon which the stars performed their slow and ancient movements, but a stage that itself neither grew nor shrank, neither began nor would ever end. To understand why this assumption felt so natural, so obvious to the scientists of that time, we might let our minds drift back even further, back to the 17th century and the quiet study of Isaac Newton, who gave humanity its first truly mathematical description of gravity and motion. Newton imagined the universe as an infinite expanse of absolute space, stretching outward in all directions without limit, populated by stars that were distributed more or less evenly throughout this endless void. In Newton's conception, which he developed over many years of careful thought and calculation, this infinite distribution of matter was necessary to prevent the universe from collapsing in upon itself. For if the universe were finite, if it had edges and boundaries, then all the matter within it would be drawn together by mutual gravitational attraction, falling inward until everything accumulated in one great central mass. But an infinite universe, Newton reasoned in his gentle and methodical way, would have no center, no preferred direction, and the gravitational pull from stars on one side would be balanced by the pull from stars on the other, leaving everything suspended in a kind of eternal equilibrium, motionless and unchanging when viewed on the larger scales. This picture of cosmic permanence persisted through the 18th and 19th centuries, becoming so familiar that it hardly needed to be stated explicitly, becoming simply the background against which all astronomical work was conducted, like the assumption that measurements would be made in ordinary numbers, or that the laws of physics would be the same tomorrow as they were today. The stars might move relative to one another in small ways, certainly, and the planets might trace their elliptical paths around the sun, and comets might come and go in their eccentric orbits, but the universe itself, the great framework containing all of these motions, was thought to be static, fixed, eternal in its basic arrangement. And yet, even within this consensus, there were small puzzles, minor curiosities that did not quite fit the picture, though they seemed too small to disturb the larger framework. One of these puzzles concerned the nature of certain fuzzy patches of light visible through telescopes, objects that astronomers called nebulae, from the Latin word for cloud or mist. Some of these nebulae showed a distinct spiral structure when observed carefully, delicate whirls of luminous material that suggested rotation or some other form of organized motion, and the question of what these spiral nebulae actually were, whether they were relatively small clouds of glowing gas within our own star system or whether they were something else entirely, something far more distant and far more vast, remained unresolved as the 19th century gave way to the 20th. There was, in fact, a long tradition of speculation about this question, dating back to the philosopher Immanuel Kant, who in 1755, more than a century and a half before the period we are now considering, had proposed that the spiral nebulae might be what he called island universes, separate systems of stars comparable in size and grandeur to our own Milky Way, but located at such immense distances that their individual stars blurred together into faint patches of undifferentiated light. Kant, writing in his study in Königsberg, had been inspired by earlier observations and by the philosophical appealing notion that the universe might contain many systems like our own, that our Milky Way might be just one island of stars among countless others, scattered through an ocean of space so vast that the distance between these islands made the distances between stars within them seem almost negligible by comparison. But Kant was a philosopher, not an astronomer, and his speculation, however prescient it might later prove to be, remained just that, a speculation, a possibility to be considered rather than a conclusion to be accepted. By the early 1900s, the island universe hypothesis had attracted some supporters among professional astronomers, but it remained controversial, contested, far from settled. The difficulty was that the telescopes of that era, impressive as they were for their time, could not resolve individual stars within the spiral nebulae, could not show whether these objects were made up of countless separate points of light, as one would expect if they were distant galaxies similar to the Milky Way, or whether they were continuous clouds of glowing gas, as one would expect if they were relatively nearby features of our own star system. The light-gathering power of even the largest telescopes was insufficient, the atmospheric blurring too severe, the photographic techniques too limited to answer this question definitively, and so the debate continued, year after year, with thoughtful astronomers on both sides marshalling evidence and arguments without reaching any final resolution. Among those who believed that the Milky Way comprised essentially the entire universe, or at least all of the universe that contained stars and organized structure, was Harlow Shapley, a young American astronomer who would later become famous for his work on determining the size and shape of our own galaxy. Shapley, working in the years just before and during the First World War, used observations of variable stars called Cepheids to estimate distances within the Milky Way, and his results suggested that our galaxy was far larger than previously thought, perhaps 300,000 light-years in diameter, a figure that seemed almost inconceivably vast, and that made it easier to believe that this single great system of stars might constitute everything there was, that the spiral nebulae, whatever they were, must be contained within this enormous Milky Way rather than existing as separate systems beyond it. Others, however, remained unconvinced. Heber Curtis, another American astronomer, argued that the spiral nebulae were indeed separate galaxies, island universes in the sense that Kant had imagined them, and that Shapley's estimate of the Milky Way size was exaggerated by various sources of error in his distance measurements. Curtis pointed to observations of novae, exploding stars, that had been detected in some of the spiral nebulae, and he noted that these novae appeared much fainter than novae observed within the Milky Way, suggesting that the spiral nebulae were at much greater distances than even the most remote parts of our own galaxy. The evidence was ambiguous, the arguments complex, and neither side could claim a decisive victory. This disagreement came to a kind of formal climax in April of 1920, when Shapley and Curtis met at the Smithsonian Institution in Washington to present their opposing views in what became known as the Great Debate, a public discussion of the scale of the universe and the nature of the spiral nebulae. The debate was cordial but substantive, each astronomer presenting the best evidence available for his position, and when it was over, the question remained unresolved, the scientific community still divided, the truth still hidden behind the limitations of existing telescopes and techniques. Both men had made valid points. Both had identified weaknesses in the other's arguments, and the audience who attended that April evening could not have known that the question they were considering would be settled within just a few years by observations made with a new and more powerful telescope, then under construction on a mountain in California. But we are moving ahead of ourselves, and there is more to consider about the static universe assumption before we turn to how it was eventually overturned. For it was not only tradition and familiarity that supported this assumption in the early 20th century, but also the most sophisticated physical theory of the time, the general theory of relativity that Albert Einstein had completed in 1915, and that represented the most profound revision of our understanding of gravity and space and time since Newton's work more than 2 centuries earlier. Einstein's general relativity described gravity not as a force acting across empty space, as Newton had imagined it, but as a curvature of spacetime itself, a bending and warping of the very fabric of the universe caused by the presence of mass and energy. This new conception was revolutionary in many ways, predicting phenomena that Newton's theory could not explain, such as the precise orbit of Mercury and the bending of starlight passing near the Sun, predictions that were confirmed by observation and that established general relativity as the best available description of gravity on cosmic scales. But when Einstein applied his equations to the universe as a whole, when he tried to construct a mathematical model of the cosmos using his new theory, he encountered a difficulty that troubled him deeply. The equations of general relativity, when applied to a universe filled uniformly with matter, did not naturally describe a static configuration. Instead, they seemed to predict that the universe should be either expanding or contracting, either growing larger with time or shrinking smaller, but not remaining the same size. This result disturbed Einstein, who shared the common assumption of his era that the universe must be static and eternal, that it could not be changing in such a fundamental way. And so, in 1917, Einstein modified his equations, adding a new term that he called the cosmological constant, represented by the Greek letter lambda, a term that introduced a kind of repulsive effect that could balance the attractive pull of gravity and allow for a static universe. The cosmological constant was not derived from any physical principle, not predicted by any other aspect of the theory, but was introduced specifically and solely to achieve the desired result of a static cosmos. Einstein was not entirely comfortable with this addition, recognizing that it was somewhat artificial, somewhat arbitrary, but he saw no other way to reconcile his theory with what he believed to be the observed fact of cosmic permanence. The influence of the Austrian physicist and philosopher Ernst Mach may have played some role in Einstein's thinking here, for Mach had emphasized the importance of relating physical concepts to observable phenomena, and the universe that astronomers observed in 1917 certainly appeared to be static, with no evidence of overall expansion or contraction that would have been detectable with the instruments and methods of that time. Mach had also raised profound questions about the nature of inertia and its relationship to the distribution of matter in the universe, questions that intrigued Einstein and influenced the development of general relativity, encouraging Einstein to think of the properties of space and time as being determined by the matter and energy within the universe rather than existing as an absolute framework independent of its contents. This perspective, sometimes called Mach's principle, was never fully incorporated into general relativity in a precise mathematical form, but it colored Einstein's approach to cosmology and reinforced his sense that the universe should be considered as a unified whole, a complete and self-consistent system whose properties were determined by all the matter it contained. And so, as the 1920s began, the scientific consensus remained firmly in favor of a static and eternal universe, despite the ambiguities surrounding the spiral nebulae and despite the slightly uncomfortable artificiality of the cosmological constant in Einstein's theory. The astronomers who observed the heavens, the physicists who theorized about the nature of space and time, and the educated public who followed their work with varying degrees of attention all shared a common picture of a cosmos that had always existed and would always continue to exist in much the same form. A picture that had prevailed for centuries and that seemed unlikely to change. But change was coming nonetheless, slowly at first, through observations made in the quiet hours of clear nights at mountaintop observatories, through measurements of the light from distant nebulae, through the careful work of dedicated scientists who did not set out to revolutionize our understanding of the universe but simply sought to record what their instruments revealed. The expansion of the universe would be discovered not through dramatic theoretical insights alone, though theory would play its essential role, but through the patient accumulation of evidence, the gradual realization that the simple picture of a static cosmos could not accommodate everything that the telescopes were showing. And all of this unfolding, this slow and gentle transformation of human knowledge about the universe and our place within it, lay just a few years ahead as the great debate concluded and the astronomers returned to their observatories to continue their work, not knowing that the answers they sought were almost within reach. In the high desert of northern Arizona, where the air is thin and dry and the stars hang with unusual clarity in the night sky, there sits an observatory that was founded with a rather particular purpose in mind. The Lowell Observatory, established in the year 1894 by the astronomer Percival Lowell, perches on a hill overlooking the small town of Flagstaff, at an elevation of more than 7,000 feet above sea level. The observatory was built primarily so that Lowell could study what he believed to be canals on the surface of Mars, a theory that has long since been set aside by the progression of scientific understanding. But the facility itself would go on to serve purposes far beyond its founder's original intentions. It was here, in this quiet outpost of astronomical inquiry, that a modest and methodical astronomer named Vesto Melvin Slipher would conduct observations that would eventually help reshape humanity's understanding of the cosmos, though the full significance of his work would not become apparent until other researchers built upon what he had so carefully measured. Vesto Slipher was born in 1875 in the state of Indiana, and he came to the Lowell Observatory in 1901 as a young man of 25, having completed his studies at Indiana University. He would remain at the observatory for his entire professional life, eventually serving as its director for more than 2 decades, and he conducted his work with a patience and precision that suited the demands of the instruments available to him. Slipher was not a man given to grand pronouncements or dramatic claims, and those who knew him described a quiet and reserved personality, someone more comfortable with the painstaking work of gathering data than with the public dissemination of bold theories. This temperament would serve him well in the years of careful observation that lay ahead, though it may also help explain why his contributions are not as widely remembered today as those of some of his more prominent contemporaries. The instrument that would enable Slipher's most important work was a spectrograph attached to the observatory's 24-inch refracting telescope. A spectrograph, for those who may find it helpful to know, is a device that takes the light gathered by a telescope and spreads it out into its component wavelengths, much as a prism separates white light into the colors of the rainbow. When astronomers examine the spectrum of light from a star or nebula, they can observe dark lines at specific positions within that rainbow of color, and these lines correspond to particular chemical elements that absorb light at those precise wavelengths. The pattern of these absorption lines serves as a kind of fingerprint, revealing the composition of the light source, but the lines can also reveal something else of considerable importance, which is whether the source of light is moving toward or away from the observer. This phenomenon is known as the Doppler effect, and it applies to light in much the same way that it applies to sound. When you stand beside a road and a vehicle approaches while sounding its horn, the pitch of the horn seems higher as the vehicle comes toward you and lower as it moves away. And this is because the sound waves are compressed as the source approaches and stretched as it recedes. Light behaves in an analogous fashion, so that when a source of light is moving toward the observer, the wavelengths are compressed and the spectral lines shift toward the blue end of the spectrum, which astronomers call a blue shift. Conversely, when the source is moving away, the wavelengths are stretched and the lines shift toward the red end of the spectrum, a phenomenon known as a redshift. By measuring how far the spectral lines have shifted from their expected positions, an astronomer can calculate the velocity at which the source is approaching or receding, a measurement known as the radial velocity. In the year 1912, Slipher turned his attention to the spiral nebulae, those faint smudges of light scattered across the night sky whose nature remained uncertain at the time. Many astronomers believed these nebulae to be clouds of gas within our own Milky Way, perhaps in the process of forming into new planetary systems, while others speculated that they might be distant systems of stars far beyond our own galaxy. Slipher did not set out to resolve this debate directly, but rather to measure the radial velocities of these objects, a task that presented formidable technical challenges. The spiral nebulae were exceedingly faint compared to individual stars, and their light was diffuse rather than concentrated in a single point, which made the process of obtaining a useful spectrum extraordinarily difficult. The spectrograph required a great deal of light to produce a clear and readable spectrum, and gathering sufficient light from these dim objects would require exposure times of remarkable length. The first nebula that Slipher chose to study was the Great Spiral in the constellation Andromeda, known to astronomers as Messier 31, or simply M31. This was among the largest and brightest of the spiral nebulae visible from the northern hemisphere, and even so, obtaining a spectrum proved to be an arduous undertaking. Slipher began his observations in the autumn of 1912, and the process required him to expose his photographic plates for many hours, sometimes accumulating more than 40 hours of exposure time spread across multiple nights. During these long exposures, the telescope had to track the nebula with exacting precision as the Earth rotated beneath the sky, and any error in the tracking would blur the spectrum and render the plate useless. The spectrograph itself was a delicate instrument that demanded careful adjustment and maintenance, and the photographic emulsions of the era were far less sensitive than those that would become available in later decades. Each plate represented an enormous investment of time and effort, and many plates had to be discarded because of imperfections or tracking errors. By September of 1912, Slipher had accumulated enough data to make a measurement, and the result he obtained was quite remarkable. The spectrum of the Andromeda Nebula showed that its absorption lines were shifted toward the blue end of the spectrum, indicating that the nebula was approaching the solar system at a velocity of approximately 300 kilometers per second. This was an unexpectedly high speed, far greater than the velocities that had been measured for most stars within the Milky Way, and it suggested that the Andromeda Nebula was moving through space with considerable energy. If the nebula were a small cloud of gas within our own galaxy, such a high velocity would be difficult to explain, and the measurement hinted that perhaps these spiral nebulae were objects of a different character altogether, though Slipher was careful not to leap to conclusions beyond what his data could support. Encouraged by this initial success, Slipher continued his program of observations, turning his spectrograph toward other spiral nebulae and accumulating measurements one painstaking exposure at a time. By 1914, he had measured the radial velocities of 15 nebulae, and a striking pattern had begun to emerge from the data. While the Andromeda Nebula was approaching, showing a blue shift, most of the other nebulae in his sample displayed redshifts, indicating that they were receding from the solar system. Some of these recession velocities were quite substantial, reaching several hundred kilometers per second, and the predominance of redshifts over blue shifts was difficult to attribute to chance. If the nebulae were simply small objects drifting randomly through the Milky Way, one would expect roughly equal numbers to be approaching and receding, but this was not what the measurement showed. The significance of these findings was not lost on the astronomical community, and when Slipher presented his results at a meeting of the American Astronomical Society in August of 1917, his colleagues responded with an enthusiasm that was unusual for such gatherings. Scientific meetings are typically subdued affairs, where researchers present their findings in measured tones, and the audience responds with polite questions and reserved appreciation. But on this occasion, Slipher received a standing ovation. The assembled astronomers recognized that his measurements represented a genuine advance in the understanding of the nebulae, even if the full interpretation of the results remained unclear. The standing ovation was a rare honor, and it reflected the technical virtuosity that Slipher had demonstrated in obtaining spectra of such faint and difficult objects, as well as the intriguing nature of the patterns that his data revealed. Slipher continued his observations over the following years, gradually expanding his catalogue of nebular velocities as the slow work of spectroscopy allowed. By 1925, he had measured the radial velocities of 45 spiral nebulae, and the pattern of predominantly recessional motion had become even more pronounced. Some of the nebulae in his expanded sample showed recession velocities of truly remarkable magnitude, with a few exceeding 1,800 kilometers per second. These were speeds far beyond anything that had been observed for objects within the Milky Way, and they posed a genuine puzzle for astronomical theory. The nebulae seemed to be fleeing from the solar system in all directions, as though the Earth occupied some central position from which the universe was expanding outward, though such an interpretation seemed both anthropocentric and physically implausible. The technical demands of this work cannot be overstated, and it is worth pausing to appreciate the patience and skill that each measurement required. The 24-inch refractor at Lowell Observatory was a fine instrument for its era, but it was modest in comparison to the larger telescopes that were beginning to come into operation at observatories in California and elsewhere. The long exposure times, sometimes extending across many nights of observation, meant that Slipher had to work with extraordinary care to ensure that each plate was properly exposed and that the spectrum was not contaminated by stray light or other sources of error. The photographic plates themselves were temperamental, sensitive to temperature and humidity and prone to developing defects if not handled properly. Reading the spectra required careful examination under magnification, measuring the positions of absorption lines to a precision of fractions of a millimeter, and converting those measurements into velocities through calculations that had to account for the characteristics of the spectrograph and the motion of the Earth itself. Despite the significance of his findings, Slipher never fully interpreted his measurements as evidence for a universal expansion of space. The theoretical framework that would eventually explain the redshifts as a consequence of cosmic expansion had not yet been developed, and Slipher was temperamentally inclined toward observation rather than speculation. He presented his data carefully and accurately, but he left the task of interpretation to others, and he did not advance bold claims about the structure of the universe based on his measurements. This reticence was characteristic of the man, who seems to have been more comfortable in the observatory dome than in the lecture hall, and who perhaps did not fully appreciate how his measurements would eventually be incorporated into a revolutionary new understanding of cosmology. In the years that followed, other astronomers would build upon the foundation that Slipher had laid. Edwin Hubble, working with the much larger telescopes at Mount Wilson Observatory in California, would combine measurements of nebula distances with velocity data, much of which had originally been collected by Slipher, to establish the relationship between distance and recession velocity that would become known as Hubble's law. This relationship would form the observational basis for the theory of the expanding universe, and Hubble would receive much of the credit and public recognition for the discovery. Slipher's contributions, while acknowledged by specialists in the field, would fade somewhat from public memory, overshadowed by the more visible achievements of his contemporaries. Vesto Slipher remained at the Lowell Observatory throughout his career, serving as director from 1916 until 1952, and he continued to contribute to astronomical research in various ways, including work on the atmospheres of planets and the rotation of galaxies. He passed away in 1969 at the age of 93, having witnessed the development of cosmology from a speculative branch of philosophy into a rigorous observational science. His measurements of the spiral nebulae, gathered over so many long nights of patient observation in the clear air of the Arizona desert, had provided essential evidence for one of the most profound discoveries in the history of human inquiry, even if his name is not always remembered alongside those of the theorists and observers who would later complete the picture. The red-shifted spectra that he recorded on his photographic plates were whispers from the depths of space, hints of a universe in motion, and though Slipher himself may not have fully grasped their ultimate significance, his careful work ensured that those whispers would eventually be heard and understood. In the year 1915, in the city of Berlin, Albert Einstein completed a work of profound mathematical beauty that would reshape humanity's understanding of space, time, and the very fabric of the cosmos, though he himself would resist some of its most remarkable implications for many years to come. The general theory of relativity, as it came to be known, described gravity not as a force that pulls objects toward one another across empty space, but rather as a curvature in the geometry of spacetime itself, a bending and warping of the invisible scaffolding upon which all events unfold. Massive objects, Einstein showed, create depressions or curves in this four-dimensional fabric, and other objects moving through spacetime simply follow the contours that these curves create, much as a marble might roll along the surface of a stretched and weighted cloth, though such analogies can only gesture toward the full mathematical elegance of what Einstein had achieved. The equations of general relativity, those 10 interconnected field equations that Einstein labored over for nearly a decade before arriving at their final form, were statements of extraordinary power and generality, capable in principle of describing the behavior of any gravitational system from the fall of an apple to the orbit of Mercury to the bending of starlight around the Sun. And yet there was one system, perhaps the most audacious of all, to which Einstein felt compelled to apply his new theory almost immediately after its completion, and that was the universe as a whole. If general relativity truly described the nature of gravity and the geometry of spacetime, then it ought to have something to say about the largest gravitational system imaginable, the totality of all matter and energy distributed throughout infinite or finite space, the cosmos in its entirety considered as a single unified object of scientific study. In 1917, Einstein published a paper with the rather understated title Cosmological Considerations in the General Theory of Relativity, a work that would become the founding document of modern theoretical cosmology, even as its central conclusion would eventually prove to be mistaken. Einstein approached the problem of the universe with certain assumptions firmly in mind, assumptions that reflected both the scientific consensus of his era and his own philosophical preferences regarding the nature of reality. He assumed, quite reasonably given the astronomical knowledge of the time, that the universe was static and eternal, neither expanding nor contracting, but simply existing in a steady state that had persisted throughout all of past time and would continue throughout all of future time. The stars and nebulae might move about in their local wanderings, but the universe as a whole, Einstein believed, must be fundamentally unchanging in its large-scale structure. There was, however, a difficulty with this assumption, a difficulty that Einstein recognized immediately upon applying his field equations to a universe filled uniformly with matter. The equations seemed to indicate that such a universe could not remain static, that the mutual gravitational attraction of all the matter within it would cause the universe to collapse inward upon itself, falling together in a cosmic implosion unless something prevented it from doing so. This was troubling to Einstein, for he could see no evidence of such a collapse in the heavens, and he felt certain that the universe must be stable and enduring. And so he introduced a modification to his original equations, an additional term that he called the cosmological constant, represented by the Greek letter lambda. This cosmological constant acted as a kind of repulsive force, a cosmic pressure that pushed outward against the attractive pull of gravity, and Einstein carefully adjusted its value so that the two effects would precisely balance one another, yielding a universe that was static and eternal, neither expanding nor contracting, held in perfect equilibrium between the inward pull of matter and the outward push of lambda. Einstein's static universe was finite but unbounded, curved back upon itself in a manner analogous to the surface of a sphere, so that a traveler journeying in any direction would eventually return to the starting point without ever encountering an edge or boundary. It was an elegant solution in many respects, satisfying Einstein's desire for a cosmos that was both comprehensible and permanent, and yet the introduction of the cosmological constant was in some ways a blemish on the mathematical purity of the original theory, an additional parameter inserted by hand rather than arising naturally from first principles. Einstein himself was never entirely comfortable with this addition, though he saw no alternative if the universe was to remain static as he believed it must. Within months of Einstein's cosmological paper, another theoretical physicist offered a quite different solution to the field equations, a solution that would prove to be of considerable importance in the years to come. Willem de Sitter was a Dutch astronomer and mathematician working at the University of Leiden, a man of quiet brilliance who had been among the first scientists outside the German-speaking world to fully appreciate the significance of Einstein's relativity theories. De Sitter had communicated Einstein's work to the British scientific community during the years of the First World War, when normal channels of academic exchange between Germany and the Allied nations had been severed, and he possessed a deep and thorough understanding of the mathematical structure of general relativity. In 1917, the same year as Einstein's cosmological paper, de Sitter published his own cosmological solution to the field equations, a solution that differed from Einstein's in one crucial respect. Where Einstein had filled his universe with matter distributed uniformly throughout space, de Sitter considered a universe that was essentially empty, containing no matter at all but retaining the cosmological constant. This might seem a peculiar choice, a universe without any stuff in it, but de Sidder's intention was to explore the mathematical possibilities inherent in the equations rather than to describe the actual cosmos in literal detail. And what he found was remarkable. De Sidder's empty universe was not static like Einstein's, but rather possessed a curious property that came to be known as the de Sitter effect. If one were to place test particles in this universe, specks of matter too small to significantly affect the overall geometry, those particles would appear to recede from one another, and the light they emitted would be shifted toward the red end of the spectrum, stretched to longer wavelengths as it traveled across the expanding space between them. The correspondence that followed between Einstein and de Sitter reveals the careful, collegial manner in which these two great minds explored the implications of their competing models. Einstein was troubled by de Sitter's solution, finding it difficult to accept a universe that exhibited expansion even in the absence of matter, and he raised various objections to the physical interpretation of de Sitter's mathematics. De Sitter, for his part, defended his solution while acknowledging its peculiarities, and the two men exchanged letters and papers debating the merits and difficulties of each approach. Einstein argued that de Sitter's model contained hidden singularities, points where the mathematics broke down in unphysical ways, while de Sitter countered that these apparent singularities were artifacts of the coordinate system rather than genuine features of the spacetime geometry. The debate was technical and subtle, conducted with mutual respect even as fundamental disagreements remained unresolved. What emerged from this exchange, and from the growing attention that astronomers and physicists paid to these cosmological models, was an awareness that the de Sitter universe made a specific observational prediction. If the actual cosmos resembled de Sitter's solution even approximately, then distant objects should exhibit redshifts, systematic displacements of their spectral lines toward longer wavelengths, and these redshifts should increase with distance. This was precisely the sort of observation that astronomers like Vesto Slipher were beginning to accumulate. Those measurements of nebula velocities that showed a preponderance of recessions rather than approaches, and some theorists began to wonder whether the de Sitter effect might explain what the telescopes were revealing. Meanwhile, in the city of Petrograd, in a Russia convulsed by revolution and civil war, a young meteorologist and mathematician named Alexander Friedmann was working on problems that would prove to be of the greatest cosmological significance, though his contributions would not be fully appreciated until after his untimely death. Friedmann had trained as a mathematician at the University of St. Petersburg before the war, had served as an aviator and bombing instructor during the conflict, and had afterward turned his attention to the mathematics of the atmosphere and, increasingly, to the mathematics of the universe. He was a man of exceptional analytical ability, comfortable with the most demanding calculations of differential geometry and tensor analysis, and he approached Einstein's field equations with fresh eyes and without the preconceptions that guided Einstein's own thinking. In 1922, Friedmann published a paper in the German physics journal Zeitschrift für Physik demonstrating that Einstein's equations admitted solutions that Einstein had apparently overlooked, solutions describing universes that were not static but dynamic, either expanding or contracting over time. Where Einstein had assumed from the outset that the universe must be unchanging and had introduced the cosmological constant to enforce this condition, Friedmann showed that the equations themselves were perfectly happy to describe a cosmos in motion, a universe whose spatial scale could increase or decrease as time progressed. This was a mathematical result of considerable generality, for Friedmann demonstrated not just one dynamic solution but an entire family of them, universes of positive curvature and negative curvature, universes with and without the cosmological constant, universes that expanded forever and universes that reached a maximum size before contracting again. Einstein's initial response to Friedman's paper was dismissive. In a brief note published in the same journal, Einstein claimed to have found a mathematical error in Friedman's calculations, an error that he believed invalidated the entire analysis. This was an understandable reaction, perhaps, from a scientist who had invested considerable effort in his static cosmological model and who was reluctant to abandon the philosophical assumptions underlying it. But it was also, as Einstein would soon discover, mistaken. Friedman wrote to Einstein explaining his calculations in greater detail and demonstrating that no error existed, and Einstein, to his credit, acknowledged this correction promptly and publicly. In 1923, Einstein published a retraction in the Zeitschrift für Physik, admitting that Friedman's results were mathematically correct and that his own earlier criticism had been unfounded. Yet even in this retraction, Einstein could not bring himself to accept the physical reality of Friedman's expanding universe. He acknowledged the mathematical validity of the dynamic solutions, while continuing to doubt that they corresponded to anything in the actual cosmos, a position that reflected his deep intuition that the universe must be static and eternal. Friedman, for his part, was content to present his work as a contribution to mathematical physics, an exploration of what the equations permitted rather than a definitive statement about the nature of reality, and he continued his research into atmospheric dynamics and cosmology from his position at the Geophysical Observatory in Petrograd, which had by now been renamed Leningrad. In 1924, Friedman published a second cosmological paper extending his analysis to universes of negative curvature, broadening still further the range of dynamic solutions he had uncovered. His work was rigorous and original, a genuine advance in theoretical cosmology, and yet it attracted relatively little attention from the broader physics community, overshadowed perhaps by the great distance between Petrograd and the centers of Western European science, and by the disruptions that continued to afflict Russian intellectual life in the aftermath of revolution. Friedman himself seemed destined for a productive career of continued discovery, but fate intervened with terrible swiftness. In the summer of 1925, while on a meteorological expedition, Alexander Friedman contracted typhoid fever, and despite the efforts of his physicians, he did not recover. He died in September of that year at the age of 37. His cosmological insights still largely unappreciated. His dynamic universes still regarded by most physicists as mathematical curiosities rather than descriptions of physical reality. It would be several more years before observations confirmed what Friedman's mathematics had foretold, and he was not alive to witness the vindication of his work. 2 years after Friedman's death, in 1927, a Belgian priest and physicist named Georges Lemaitre independently derived the equations of an expanding universe, unaware of the Russian mathematician's earlier work. Lemaitre had studied at the University of Cambridge and the Massachusetts Institute of Technology, had worked with the astronomer Harlow Shapley at Harvard, and brought to the cosmological problem both mathematical sophistication and direct familiarity with the observational data on nebular redshifts. His paper, published in a relatively obscure Belgian journal, combined theoretical derivation with empirical analysis, relating the expansion of space to the observed velocities of distant nebulae in a manner more explicit than any previous treatment. Like Friedman, Lemaitre showed that Einstein's equations naturally accommodated a dynamic cosmos, and like Friedman, he would wait some time before his contribution received the recognition it deserved, But the theoretical foundation for understanding the expanding universe was now firmly in place, awaiting only the observational confirmation that would soon arrive from the great telescopes of California. High above the city of Los Angeles, where the San Gabriel Mountains rise gently from the sprawling basin below, there stands a white dome that for more than 3 decades held within it the most powerful eye humanity had ever turned toward the heavens. This is Mount Wilson Observatory, and within that dome rested the Great Hooker Telescope, a remarkable instrument that would transform our understanding of the cosmos in ways that even its creators could scarcely have imagined when construction began in the early years of the 20th century. The story of this telescope is one of patience and persistence, of engineering challenges overcome through careful work, and of the quiet dedication of those who spent long, cold nights gathering the faint light of distant stars and nebulae onto glass photographic plates. The visionary behind Mount Wilson Observatory was George Ellery Hale, an American astronomer whose gentle persistence and remarkable ability to inspire wealthy benefactors would lead to the construction of 4 of the world's largest telescopes during his lifetime. Hale was born in Chicago in 1868, and from his earliest years he displayed an intense fascination with the sun and stars. As a young man, he invented a device called the spectroheliograph, which allowed astronomers to photograph the sun in the light of a single wavelength, revealing details of solar activity that had never before been visible. This early work on the sun would remain a passion throughout his life, even as his attention expanded to encompass the distant reaches of the universe. Hale understood, perhaps better than anyone of his generation, that progress in astronomy depended upon building ever larger telescopes. A larger mirror gathers more light, and more light means that fainter and more distant objects become visible to the patient observer. He had already overseen the construction of the 40-inch refracting telescope at Yerkes Observatory in Wisconsin, which remains to this day the largest refractor ever used for astronomical research. But Hale knew that the future belonged to reflecting telescopes, which use curved mirrors rather than lenses to gather and focus light. Mirrors can be made larger than lenses without the same problems of weight and optical distortion. And so Hale set his sights on building the greatest reflecting telescope the world had ever seen. The site he chose was Mount Wilson, a peak in the San Gabriel Mountains that rises to an elevation of 5,715 feet above sea level. Hale had first visited this mountain in 1903, and he immediately recognized its exceptional qualities for astronomical observation. The altitude places the observatory above much of the atmospheric turbulence that blurs the images seen by telescopes at lower elevations. The climate of Southern California provides an abundance of clear nights throughout the year, and the particular conditions of the atmosphere above Mount Wilson prove to be remarkably steady, producing what astronomers call good seeing, which refers to the stillness of the air through which starlight must travel on its journey to the telescope mirror. Before the great 100-inch telescope could be contemplated, Hale first established a 60-inch reflector on the mountain, which saw first light in 1908 and was itself the largest operational telescope in the world at that time. But even as the 60-inch was being completed, Hale was already planning something far more ambitious. He envisioned a telescope with a mirror 100 inches in diameter, a vast sheet of glass that would gather nearly 3 times as much light as the 60-inch and allow astronomers to peer deeper into space than ever before. To fund this enormous undertaking, Hale approached John D. Hooker, a Los Angeles businessman who had made his fortune in hardware and who possessed a genuine interest in scientific advancement. Hooker agreed to provide the funds necessary to cast and grind the Great Mirror, a donation that would eventually amount to $45,000, and in recognition of his generosity, The telescope would bear his name for all the years to come. The Carnegie Institution of Washington provided additional funding for the construction of the mounting, the dome, and the supporting infrastructure that such an instrument would require. The creation of the mirror itself would prove to be one of the most challenging aspects of the entire project, and at several points it seemed as though the difficulties might prove insurmountable. Hale contracted with the Saint-Gobain Glassworks in France, a company with centuries of experience in the manufacture of fine glass, to cast the enormous mirror blank. The mirror would need to be made from a special type of glass with a very low coefficient of thermal expansion, so that it would not change shape as the temperature varied through the long, cold nights of observation. The blank would weigh approximately 4.5 tons and would need to be cast in a single piece without flaws or bubbles that might compromise its optical quality. The first attempt at casting the mirror in 1908 was unsuccessful, producing a blank filled with bubbles and imperfections that made it unsuitable for use. A second attempt also failed to meet the exacting standards required. It was not until 1912 that Saint-Gobain succeeded in producing a mirror blank that Hale deemed acceptable, though even this piece contained some bubbles near the surface that caused considerable concern. There were genuine worries that these imperfections might render the mirror unusable, but Hale made the decision to proceed, hoping that careful grinding and polishing would remove enough material to eliminate the worst of the flaws while still leaving sufficient glass for the finished mirror. The journey of the mirror blank from France to California was itself a considerable undertaking. The massive disk of glass crossed the Atlantic Ocean by steamship and then traveled by rail across the North American continent to Pasadena. From there, it faced perhaps the most challenging leg of its journey, the ascent of Mount Wilson itself. The road to the summit had been constructed specifically to allow the transport of telescope components, winding its way up the mountainside in a series of gentle switchbacks that added miles to the direct distance but reduced the steepness of the grade. Even so, transporting the 4.5-ton mirror up this road required careful planning and the use of a specially designed truck that could navigate the narrow turns while bearing its precious cargo. Once the mirror blank reached the summit, it entered the optical shop where it would spend the next years being slowly ground and polished into its final parabolic shape. George Ritchie, a skilled optician who had worked with Hale for many years, oversaw this delicate process, removing material fraction by fraction until the surface of the mirror matched the precise mathematical curve required to bring distant starlight to a perfect focus. The grinding and polishing took several years, and throughout this time, construction continued on the massive steel mounting that would hold the mirror and allow it to track the stars as they wheeled slowly across the sky. One of the great concerns during the design and construction of the telescope was whether the mirror might sag under its own weight. Glass, though it appears rigid to our everyday experience, does in fact flow very slowly over long periods of time, and even over shorter periods. A mirror as large and heavy as the hooker might deform slightly as it pointed toward different parts of the sky. To address this concern, the engineers designed an elaborate support system consisting of numerous small pads that would bear the weight of the mirror and could be adjusted to maintain its proper shape regardless of its orientation. This support system proved effective, and the mirror maintained its figure with sufficient accuracy to produce the sharp images that astronomers required. The dome that houses the Hooker telescope is itself a remarkable structure, measuring 100 feet in diameter and rising to a height that dominates the summit of Mount Wilson. The dome can rotate smoothly to allow the telescope to point toward any part of the sky, and a large slit in its surface opens to admit the light of the stars. The dome was not heated, as the presence of warm air within the observing chamber would create turbulence that would blur the images. This meant that astronomers working through the night would experience the full cold of the mountain air, which could drop well below freezing during winter observations. On the night of November 1st, 1917, the Great Telescope saw first light, though the occasion was not without its anxieties. When the mirror was first exposed to the night sky, the images of stars appeared distorted and unfocused, leading to fears that the mirror was indeed flawed and that the years of work had been in vain. However, it was soon realized that the mirror had not yet cooled to the ambient temperature of the night air, and the distortions were caused by thermal effects rather than any permanent defect. As the night progressed and the mirror slowly equilibrated, the images sharpened, and by the early hours of the morning, the telescope was revealing details of celestial objects with a clarity that exceeded all expectations. The working conditions for astronomers at Mount Wilson were demanding, requiring both physical endurance and meticulous attention to detail. Observers would spend entire nights in the unheated dome, guiding the telescope and exposing photographic plates to the faint light of distant nebulae and stars. The exposures might last for hours, and throughout this time, the astronomer would need to make constant small adjustments to keep the telescope tracking precisely, compensating for any irregularities in the clockwork drive mechanism. The cold was a constant companion, and observers learned to dress warmly and to take precautions against the numbness that could affect their fingers and impair their ability to work the delicate controls. The photographic plates themselves required careful handling and processing. Each glass plate was coated with a light-sensitive emulsion, and after exposure, it would be developed in the darkroom to reveal the images it had captured. These plates became permanent records of the observations, and astronomers would spend many hours examining them with magnifying devices, measuring the positions and brightnesses of stars, and studying the spectra of light that revealed the composition and motion of distant objects. The plate collection at Mount Wilson would eventually number in the tens of thousands, representing decades of patient observation. Among those who worked at Mount Wilson, perhaps none had a more remarkable trajectory than Milton Humason, who came to the observatory not as a trained scientist, but as a mule driver on the pack trains that hauled supplies up the mountain road during the construction years. Born in 1891, Humason had only an 8th grade education, but he possessed an innate understanding of the night sky and an extraordinary patience that would prove invaluable in the demanding work of astronomical observation. After working as a mule driver, he took a position as a janitor at the observatory, and it was in this capacity that he first came to the attention of the astronomers. Humason's careful nature and obvious fascination with the work being done at the observatory led to his gradual advancement. He learned to assist with observations, and over time, his skill at guiding the telescope and obtaining photographs of the faintest and most challenging targets became legendary among his colleagues. Despite his lack of formal training, he was eventually appointed to the scientific staff, and he would go on to make contributions to astronomical research that any university-trained astronomer would have been proud to claim. His ability to obtain spectra of extremely faint nebulae, requiring exposures that sometimes stretched over multiple nights, would prove essential to the discoveries that followed. In addition to the great nighttime telescopes, Mount Wilson was also home to important instruments for studying the sun. Hale's lifelong interest in solar physics led to the construction of tower telescopes designed specifically for observing the sun in exquisite detail. These towers rose high above the ground to escape the turbulent air heated by the sunlit terrain, and they contained instruments that could analyze the light of the sun to reveal the presence of magnetic fields in sunspots and the chemical composition of the solar atmosphere. Hale's discovery that sunspots are regions of intense magnetic activity was made using these solar telescopes, a finding that fundamentally changed our understanding of the sun and established the field of solar magnetism. By the 1920s, Mount Wilson Observatory had become the undisputed center of observational astronomy, the place where the most important questions about the nature of the universe were being addressed with the most powerful instruments available. The combination of the 100-inch Hooker telescope, the skilled observers who worked its mechanism through countless freezing nights, and the steady atmospheric conditions of the California mountains created an environment in which fundamental discoveries could be made. The telescope would hold its position as the largest in the world until 1949, when the 200-inch Hale telescope, named in honor of George Ellery Hale, saw first light on Palomar Mountain, carrying forward the tradition of ever larger instruments that Hale had championed throughout his life. And so the great telescope stood ready, its mirror polished to a precise curve, its mounting engineered to track the stars with smooth precision, its dome open to the clear mountain sky. The observers who climbed the stairs to the Newtonian focus or settled into the Cassegrain cage were about to embark on a series of observations that would reveal the true scale and nature of the universe, transforming human understanding in ways both profound and humbling. But that work proceeded quietly, one photographic plate at a time, through long and patient nights in which the cold was merely an inconvenience to be endured and the faint light of distant galaxies slowly impressed itself upon the emulsion, carrying information across vast reaches of space to the careful eyes and minds that waited to receive it. Edwin Hubble came to astronomy by a winding path, one that carried him through several quite different lives before he settled into the work that would reshape our understanding of the cosmos. He was born in 1889 in Marshfield, Missouri, a small town where his father worked in the insurance business, and from an early age he showed the sort of athletic and academic promise that tends to draw attention in American communities. He grew tall and strong, excelling in track and field, in basketball, and most notably in boxing, where his physical presence and quick reflexes made him a formidable competitor. By the time he reached the University of Chicago, he had developed into what observers described as an imposing young man, someone who carried himself with a certain deliberate confidence that would remain characteristic throughout his life. At Chicago, Hubble studied mathematics and astronomy, but he also proved himself capable in other directions, and upon graduation he was awarded a Rhodes Scholarship to study at Oxford University in England. This was a significant honor, one that placed him among a select group of American students chosen each year to pursue further education at one of the oldest universities in the world. At Oxford, however, he did not continue with astronomy. Instead, following what he later described as a promise made to his father, he read for a degree in jurisprudence, which is to say he studied law, and he also took courses in literature and Spanish. The years at Oxford left a lasting impression on him, most visibly in the affected British mannerisms and speech patterns that he would maintain for the rest of his life, a cultivated accent and a certain formality of expression that some colleagues found charming and others found rather puzzling in a man from Missouri. Upon returning to the United States, Hubble briefly practiced law in Louisville, Kentucky, but he found the work unsatisfying, and after about a year he acknowledged what had perhaps been evident all along, that his true interests lay in the study of the heavens. He returned to the University of Chicago to pursue a doctorate in astronomy, working at the Yerkes Observatory in Williams Bay, Wisconsin, where he studied faint nebulae, those hazy patches of light scattered across the sky whose nature remained deeply uncertain. His doctoral thesis, completed in 1917, examined these objects photographically, measuring their positions and brightness, though at that time he could not yet determine whether they lay within our own stellar system or far beyond it. Before Hubble could take up a position at a major observatory, the United States entered the First World War, and he enlisted in the Army, eventually serving as an officer and reaching the rank of major before the conflict ended. He saw deployment to France, though he arrived too late to see significant combat, and after the armistice he remained in Europe for a time before finally returning to civilian life. It was in 1919, at the age of 29, that Edwin Hubble arrived at Mount Wilson Observatory in the mountains above Pasadena, California, where the largest telescope in the world awaited him, and where he would spend most of the rest of his career. The 100-inch Hooker telescope at Mount Wilson was a remarkable instrument. Its mirror gathered more light than any other telescope then in existence, and it was capable of revealing details in faint celestial objects that had never before been visible to human eyes. Hubble understood immediately the potential of this great telescope, and he set about a systematic program of photographing the spiral nebulae, those peculiar objects that appeared through smaller instruments as pale whirlpools of light. The question of what these spiral nebulae actually were had occupied astronomers for decades, with some arguing that they were merely clouds of gas within our own Milky Way galaxy, and others suggesting that they might be entirely separate stellar systems, island universes lying at tremendous distances from our own. For several years Hubble worked patiently at Mount Wilson, taking long photographic exposures of the nebulae night after night, building up a collection of glass plates that recorded the positions and brightness of countless faint stars and nebulous patches. He was methodical in his approach, careful not to draw conclusions before the evidence warranted them, and he developed a reputation among his colleagues for thoroughness and precision, even if some found his personal manner somewhat aloof or self-regarding. Then, in October of 1923, while examining a photographic plate of the Great Spiral Nebula in the constellation Andromeda, Hubble noticed something that would prove to be of the highest significance. On the plate he identified what appeared to be a nova, one of those stars that suddenly flares to great brightness before fading again, and he marked the position with the letter N to indicate his finding. But as he compared this plate with earlier exposures of the same region, he realized that the star was not a nova at all, for it was varying in brightness in a regular, periodic manner, growing brighter and then fainter and then brighter again over a span of days. This was not the behavior of a nova, but rather of a Cepheid variable star, a type of pulsating star whose properties had been carefully studied over the preceding decades. Hubble crossed out the N on his plate and wrote instead the abbreviation VAR, marking what he now understood to be a variable star of the Cepheid type, and the plate bearing this correction would later become one of the most celebrated artifacts in the history of astronomy. The reason that Cepheid variable stars were so important, the reason that Hubble immediately understood the significance of his discovery, lies in the work of Henrietta Leavitt, an astronomer who had worked at the Harvard College Observatory in the early years of the 20th century. Leavitt was one of a group of women employed at Harvard to examine photographic plates and catalogue the positions and properties of stars, work that was considered suitable for women at a time when they were largely excluded from using the telescopes themselves. Her particular assignment involved studying variable stars in the Small Magellanic Cloud, a fuzzy patch of light visible in the southern hemisphere that we now know to be a small galaxy orbiting our own. In 1908, and then more fully in 1912, Leavitt published her discovery that among the Cepheid variables in the Small Magellanic Cloud, there existed a clear relationship between the period of a star's brightness variation and its intrinsic luminosity. Stars that took longer to complete their cycle of brightening and dimming were, she found, genuinely more luminous than those with shorter periods. This was a relationship of profound importance, for it meant that if one could measure the period of a Cepheid variable, one could deduce how intrinsically bright the star actually was, and by comparing this intrinsic brightness with the star's apparent brightness as seen from Earth, one could calculate how far away it must be. The period-luminosity relationship, as it came to be called, transformed Cepheid variables into what astronomers sometimes describe as standard candles, objects whose true brightness is known and which can therefore serve as distance indicators across the vastness of space. Henrietta Leavitt herself did not have the opportunity to apply her discovery to determine the distances to far objects, for the culture of the observatory at that time reserved such interpretive work for male astronomers, and her own life was cut short by illness in 1921. But her period-luminosity relationship became an essential tool for those who came after her, and it was precisely this tool that Edwin Hubble now held in his hands as he examined his photographic plate of the Andromeda Nebula. By measuring the period of the Cepheid variable he had discovered in Andromeda, Hubble could use Leavitt's relationship to determine the star's intrinsic luminosity, and from its apparent faintness he could then calculate how far away it must lie. The result was startling. The Cepheid in Andromeda, and therefore Andromeda itself, appeared to be at a distance of approximately 900,000 light-years from Earth, a distance so great that it placed the nebula far beyond the boundaries of the Milky Way galaxy. If this measurement was correct, then Andromeda could not possibly be a cloud of gas within our own stellar system. It had to be a separate galaxy, an island universe in its own right, containing billions of stars and lying at an almost incomprehensible remove from our own cosmic neighborhood. Hubble was cautious by nature, and he did not rush to publish his findings. He continued to gather more data, identifying additional Cepheid variables in Andromeda and in other nebulae, checking and rechecking his measurements, refining his distance calculations. Finally, in January of 1925, he allowed his results to be announced at a meeting of the American Astronomical Society, though he did not attend the meeting himself. A colleague read his paper aloud to the assembled astronomers, presenting the evidence that the spiral nebulae were external galaxies lying hundreds of thousands or even millions of light-years beyond the Milky Way. The great debate that had occupied astronomers for so many years was effectively settled, and the universe had suddenly become vastly larger than most had imagined. Among those who received the news with mixed feelings was Harlow Shapley, who had by then moved from Mount Wilson to become director of the Harvard College Observatory. Shapley had made his own significant contributions to measuring the scale of the Milky Way, using Cepheid variables to determine that our galaxy was far larger than previously supposed, but he had also argued strenuously against the idea that the spiral nebulae were external galaxies. He had staked his reputation on the position that the Milky Way encompassed essentially all that existed, that the spiral nebulae were relatively nearby objects within our own system, and Hubble's discovery now contradicted this view in the most direct possible manner. The relationship between the two men was never warm, colored by professional rivalry and perhaps also by differences in temperament and background, and it would remain somewhat strained throughout their careers. We should note that Hubble's original distance estimate for Andromeda, though revolutionary in its implications, was not entirely accurate by modern standards. We now know that the Andromeda galaxy lies at a distance of approximately 2.5 million light-years, nearly 3 times farther than Hubble calculated. The discrepancy arose in part because the calibration of the period-luminosity relationship was not yet fully refined, and in part because astronomers at that time did not yet fully account for the effects of interstellar dust, which dims the light of distant objects and can cause distances to be underestimated. Nevertheless, Hubble's fundamental conclusion was correct, The spiral nebulae were indeed external galaxies, and his work opened the door to an entirely new understanding of the cosmos. Having established that galaxies existed beyond our own, Hubble turned his attention to classifying them according to their shapes and structures. In 1926, he published a classification system that organized galaxies into several broad categories based on their appearance in photographs. Elliptical galaxies were those that appeared as smooth, featureless ovals of light, ranging from nearly spherical to highly elongated in shape. Spiral galaxies showed the characteristic pinwheel structure, with curved arms of stars and gas winding outward from a central bulge. Within the spiral category, Hubble distinguished between ordinary spirals and barred spirals, the latter possessing a distinct bar-shaped structure passing through the center from which the spiral arms emerged. Finally, there were irregular galaxies, those that fit none of the other categories and displayed no obvious symmetry or structure. This classification scheme, sometimes represented visually as the Hubble tuning fork diagram, remains in use today with various refinements, and it provided astronomers with a common vocabulary for describing the diversity of galaxies scattered throughout the universe. Hubble himself was careful not to suggest that his classification represented an evolutionary sequence, though some astronomers at the time speculated that galaxies might evolve from one type to another over cosmic time. He preferred to present his observations without excessive theoretical interpretation, letting the data speak for itself, and this restraint was characteristic of his approach to scientific publication throughout his career. In his writings and public presentations, Hubble cultivated an image of careful objectivity, avoiding speculative claims and confining himself to what the observations could directly support. His prose style was measured and precise, and he tended to present his discoveries as the natural outcome of systematic investigation rather than as dramatic breakthroughs. Whether this reflected genuine modesty or a more calculated presentation of self is difficult to say, but it contributed to his reputation as a rigorous and reliable observer. His affected British accent and formal manner, acquired during his Oxford years and maintained throughout his life, added to the impression of scholarly detachment, and he moved comfortably in the social circles of Pasadena, forming friendships with writers and artists and other notable figures who were drawn to the glamour of the great telescope on the mountain. By the mid-1920s, Edwin Hubble had established himself as one of the foremost astronomers in the world, the man who had revealed that the universe extended far beyond the boundaries of our own galaxy, that it was populated by countless other stellar systems scattered through an immensity of space that the human mind could scarcely comprehend. Yet his most profound discovery still lay ahead, waiting to be drawn from the same photographic plates and the same careful measurements that had already transformed our understanding of the cosmos. And now we turn to one of the most unlikely journeys in the history of astronomy, a story that unfolds with the quiet steadiness of the mountain itself, where a young man who never finished school would eventually help measure the distances to the farthest objects then known to science. This is the story of Milton Lazel Humason, and it begins not with telescopes or universities, but with mules, the winding dirt roads of Mount Wilson, and the patient, unhurried work of hauling supplies up a mountainside in the early years of the 20th century. Milton Humason was born in Dodge Center, Minnesota, in August of 1891, though his family soon moved to the warmer climate of California, where he would spend the rest of his long and remarkable life. As a boy, he attended school like any other child, but his formal education came to an end after the 8th grade, when he was perhaps 14 years old, and the reasons for this were various and ordinary, the kind of circumstances that quietly redirect so many lives without fanfare or drama. There was no singular moment of decision, no grand departure, simply the gradual turning away from classrooms and textbooks toward the practical work of making a living with one's hands. And in this way, young Milton Humason stepped away from the path that might have led to university lecture halls and stepped instead onto the dusty trails of the San Gabriel Mountains. It was around 1905 or 1906 that Humason first came to Mount Wilson, that same mountain where George Ellery Hale was building his great observatory, and the connection was made through a summer camp that operated in the area, a place where Humason worked as a bellboy and general helper. The mountain captivated him, as it captivated so many who spent time in its forests and clearings, with the crisp air and the endless views and the particular quality of silence that one finds only at elevation, where the sounds of the valley below fade to nothing and the sky at night reveals itself in all its depth and stillness. Humason fell in love with the mountain, and he decided that he would find a way to stay. The opportunity came through the mule teams that were then essential to the observatory's construction, for in those years before paved roads reached the summit, every piece of equipment, every length of timber, every crate of supplies had to be hauled up the steep and winding trails by pack animals, and this work required drivers who understood mules and who could navigate the treacherous paths without losing their cargo or their animals. Milton Humason became one of these drivers, handling the teams with the patience and steadiness that would later characterize all his work, learning the mountain's contours intimately, becoming as much a part of Mount Wilson as the trees and the rocks themselves. He was perhaps 17 or 18 years old, with no thought of astronomy, no knowledge of spectroscopy, simply a young man doing physical labor under the California sun, earning his living one trip at a time. The years passed in this way, and Humason married the daughter of the observatory's chief engineer, a connection that would prove significant, though it was made through simple human affection rather than professional calculation. When the construction work eventually wound down and the mule teams were no longer needed in such numbers, Humason might have drifted away from the mountain, might have found work elsewhere and lived out his days in some other occupation entirely, but instead he found a position as a janitor at the observatory, sweeping floors and cleaning equipment and generally making himself useful in whatever way was required. This was humble work, the kind of labor that passes unnoticed by most, but it kept him on the mountain he loved, and it placed him in daily contact with the astronomers and their instruments, and perhaps without fully realizing it, Milton Humason was beginning his education in a different kind of school. The astronomers noticed things about the janitor, small things at first but significant ones. They noticed that he was curious about the instruments, that he asked thoughtful questions, that he seemed to understand intuitively the delicate nature of the equipment and handled everything with care and precision. They noticed his reliability, his willingness to work long hours without complaint, his calm demeanor in the face of difficulties. Gradually, almost imperceptibly, his duties began to shift, and he found himself assisting with the observations themselves, helping to set up equipment, learning the routines of the telescope operators, absorbing knowledge through proximity and practice rather than through formal instruction. By around 1917 or 1918, Humason had become a night assistant, working alongside the astronomers during their long observing sessions, and it was here that his exceptional natural abilities began to reveal themselves. Astrophotography in those days was a demanding art, requiring not merely technical knowledge but a particular kind of physical and mental stamina that few possessed. The photographic plates of the era were slow, far less sensitive than modern instruments, and capturing the faint light of distant objects required exposures that might last for hours, sometimes spreading across multiple nights as conditions allowed. During these long exposures, the telescope had to track the apparent motion of the stars across the sky with perfect precision, and this tracking was not automatic in the way we might imagine today, but required constant human attention and small manual corrections, tiny adjustments made by watching a guide star through a separate eyepiece and keeping it centered through subtle movements of the controls. This work was exhausting and unforgiving, demanding intense concentration over periods that might stretch to 4 or 5 hours without interruption, and a single lapse in attention, a single uncorrected drift of the guide star, could ruin an entire night's work. Milton Humason proved to be extraordinarily gifted at this painstaking labor. His hands were remarkably steady, his patience seemingly infinite, his ability to maintain focus through the coldest and longest nights almost supernatural in its consistency. The dome of the 100-inch telescope was unheated, kept at outside temperature to prevent air currents that would blur the images, and observers would work through winter nights at temperatures well below freezing, bundled in heavy clothing with their breath visible in the dim light, fighting drowsiness and cold and the particular kind of fatigue that comes from holding utterly still while remaining utterly alert. Humason thrived in these conditions, finding in the quiet discipline of the work a kind of meditation, a deep satisfaction in doing something difficult with consummate skill. The astronomers began to trust him with increasingly important observations, and his natural abilities led to ever greater responsibilities. By the early 1920s, he was being given serious scientific work to perform, though he still lacked any formal credentials, any degree or certificate that might have legitimized his position in the eyes of the wider astronomical community. George Eloy Hale, who directed the observatory and who had spent his career building institutions and recruiting talent, recognized in Humason something that could not be taught in any classroom, and in 1919 he appointed Humason to the regular staff, a decision that raised some eyebrows among the more credentialed astronomers but which would be vindicated many times over in the decades to come. It was in 1928 that the partnership began which would produce some of the most important astronomical measurements of the 20th century, when Edwin Hubble enlisted Milton Humason's help in a systematic campaign to measure the recession velocities of distant galaxies. Hubble had his own formidable skills, particularly in identifying Cepheid variable stars and calculating distances, but the spectroscopic work of measuring redshifts required the very best in photographic technique, and Humason was simply the best there was. The division of labor that emerged was natural and efficient, with Hubble determining distances using his methods and Humason obtaining the spectra from which velocities could be calculated, each man contributing what he did best to the larger enterprise. The physical demands of this work were considerable, and they fell primarily on Humason, who would spend night after night on the observing platform of the great telescope, riding the moving structure as it tracked across the sky, guiding the exposures with his characteristic precision. The 100-inch telescope was a massive instrument, and the observer's cage where Humason worked was mounted near the top of the tube, some 50 or 60 feet above the floor of the dome, swaying gently as the telescope moved, exposed to whatever temperature the night provided. There were no conveniences, no heat, no comfortable chair, only the eyepiece and the guiding controls and the cold metal of the telescope structure and the immense darkness of the dome overhead. Humason would remain at his post for hours at a stretch, maintaining focus on a tiny guide star while the precious photons from some impossibly distant galaxy accumulated slowly on his photographic plate. And when the night was done, he would develop the plate himself, examine the results, and begin planning the next observation. The spectra that Humason obtained pushed steadily into new territory, revealing recession velocities far greater than any previously measured. In 1929, the same year that Hubble published his famous paper on the velocity-distance relation. Humason measured the spectrum of a galaxy called NGC 7619, a fuzzy patch of light in the constellation Pegasus, and found that it was receding at a velocity of approximately 3,779 kilometers per second, the fastest recession yet recorded for any celestial object. This was an extraordinary number, implying that this one galaxy was rushing away from us at a speed that would carry it across the diameter of Earth's orbit in roughly 4 minutes, a velocity so large as to seem almost absurd. And yet there it was, recorded on the photographic plate by a man who had never attended high school. And Humason kept pushing further, kept obtaining spectra of ever more distant objects, kept extending the reach of human measurement deeper into the cosmos. The work was never easy, each new target presenting its own challenges, each faint smear of light requiring its own extended campaign of observation and analysis. By 1931, Humason had measured velocities exceeding 20,000 kilometers per second, and by 1936, working with the accumulated data from years of patient observation, he had pushed the measurements to roughly 40,000 kilometers per second, velocities so enormous that the very light from these objects had been stretched substantially toward the red end of the spectrum, shifted by the expansion of space itself. These measurements provided the observational foundation for the expanding universe, the evidence that supported the theoretical frameworks being developed by Lemaitre and others, and they bore the unmistakable mark of Humason's extraordinary skill. There were those in the astronomical community who found it difficult to accept that such important work was being done by a man without proper credentials, a man who had driven mules and pushed a broom and learned his trade not through the proper channels of academia but through the informal apprenticeship of the observatory floor. Some dismissed his early work, questioned his methods, suggested that surely an 8th grade dropout could not be producing reliable scientific data. But the results spoke for themselves, with their precision, their consistency, their agreement with other measurements and with theoretical expectations, and gradually even the skeptics were forced to acknowledge that Milton Humason was simply one of the finest observers who had ever lived, formal education or no. His personality helped smooth the way through these professional difficulties, for where Edwin Hubble could be aloof and formal and conscious of his own importance, Humason was warm and approachable and apparently unconcerned with matters of status and recognition. He made friends easily, enjoyed conversation and laughter, and bore no grudges against those who had doubted him. The two men made an odd pair, the ambitious and cultivated Hubble with his affected British manner and his careful attention to his own reputation, and the unpretentious Humason with his practical skills and his easy way with people. But their partnership was extraordinarily productive, each man's strengths complementing the other's, and together they accomplished more than either could have alone. The recognition that Humason deserved came eventually, though it came through channels that bypassed the formal credentialing he had never obtained in his youth. In 1950, Lund University in Sweden awarded him an honorary doctorate, acknowledging in this way the contributions he had made to human knowledge, the countless hours of patient observation, the steady hands and clear eyes that had captured the light of galaxies so distant that their light had been traveling toward us since long before the first humans walked the earth. For a man who had left school at 14, who had learned his trade by watching and doing rather than by studying and examination, this honor meant a great deal, though those who knew him say that he wore it lightly, with the same lack of pretension that had characterized his entire career. Milton Humason continued working at Mount Wilson for many years, eventually moving to the newer and larger telescopes at Palomar Mountain as well, always observing, always collecting the light of distant objects, always contributing to our understanding of the universe's vast scale and its fundamental nature. He lived until 1972, long enough to see the expansion of the universe become established science, long enough to see new generations of astronomers build upon the foundation he had helped create. And when he died, he left behind not theories or equations but data, thousands upon thousands of observations, the patient work of a lifetime spent measuring the heavens with precision and care. And so we remember Milton Humason, the mule driver who measured the universe, whose journey from the dusty trails of Mount Wilson to the very forefront of cosmological research reminds us that talent and dedication can sometimes matter more than credentials, that the quiet virtues of patience and steadiness and attention to detail can contribute as much to human knowledge as any flash of theoretical brilliance. His hands guided the great telescopes through countless cold nights. His eyes watched the guide stars with unfailing attention, and the spectra he captured on his photographic plates helped reveal that we live in a universe that is expanding, that the galaxies are receding, that the cosmos is vaster and stranger than anyone had previously imagined. This is a restful thing to know, as you settle deeper into comfort and let your breathing slow, that such important discoveries were made not through drama or crisis but through the accumulated work of many quiet nights, one exposure at a time, one galaxy at a time, with patience and care and the steady hands of a man who loved his mountain and found his calling in its cold, clear air. In the year 1929, Edwin Hubble published a paper that would quietly change our understanding of the cosmos, though at the time it appeared as a modest contribution tucked into the pages of the Proceedings of the National Academy of Sciences, running to just 2 pages in length, with a single graph and a table of data that seemed almost too simple to carry the weight of such a profound implication. The paper bore the title A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae, and in it Hubble presented evidence that the galaxies of the universe appeared to be moving away from us at speeds that increased in proportion to their distance, a finding that would eventually lead to our modern understanding of an expanding universe, though Hubble himself was careful not to make such grand claims in his measured and deliberately cautious prose. The data that Hubble assembled for this paper came from 2 distinct sources, woven together into a single coherent picture through his careful analysis at Mount Wilson Observatory in the mountains above Pasadena, California. The distances to the galaxies, which Hubble still referred to as nebulae in keeping with the terminology that was only gradually shifting in those years following his 1924 announcement, came from his own painstaking observations using the 100-inch Hooker telescope, the largest and most powerful instrument of its era. He had measured these distances primarily through the identification of Cepheid variable stars in the nearer galaxies, those pulsating beacons whose regular brightening and dimming revealed their true luminosity and thus their distance from Earth. And for the more distant objects, he relied on the brightness of what he took to be the most luminous stars visible within each galaxy, assuming that the brightest stars in one galaxy would be comparable to the brightest stars in another. The velocities, on the other hand, came largely from work that had been conducted over the preceding 2 decades by Vesto Melvin Slipher at the Lowell Observatory in Flagstaff, Arizona, who had spent years carefully measuring the spectral shifts of spiral nebulae and had found that the vast majority of them showed their light shifted toward the red end of the spectrum, indicating motion away from Earth at considerable speeds. Slipher had published these velocity measurements in various papers and had presented them at astronomical meetings, where they had been received with interest and some puzzlement, for it was not immediately clear what it meant that nearly all of these distant objects seemed to be receding from us. Hubble made use of these velocities in his 1929 paper, incorporating the measurements that Slipher had so carefully obtained. Though the paper itself did not prominently acknowledge Slipher's contribution, a matter that has troubled some historians of science who feel that Slipher's foundational work deserved more explicit recognition in the document that would come to be seen as announcing one of the great discoveries of modern cosmology. In total, Hubble's paper presented data for 46 galaxies, though the quality and reliability of these measurements varied considerably from one object to the next. For only a handful of these galaxies did Hubble have what he considered reliable Cepheid-based distances, and for the more distant objects he was forced to rely on less certain methods that introduced considerable uncertainty into his calculations. The velocities ranged from relatively modest values of a few hundred kilometers per second up to around 1,000 kilometers per second for the most distant objects in his sample. And when Hubble plotted these velocities against the corresponding distances, he found that despite the considerable scatter in the data points, there was a clear tendency for the more distant galaxies to have higher recession velocities, a pattern that suggested a linear relationship between the two quantities. The relationship that Hubble identified can be expressed in a simple mathematical form, stating that the velocity at which a galaxy recedes from us is equal to its distance multiplied by a constant factor, which has come to be known as the Hubble constant and is typically denoted by the symbol h with a subscript 0. If we write this relationship as v equals h naught times d, where v represents the recession velocity and d represents the distance, then the Hubble constant tells us how much faster a galaxy is moving away for each additional unit of distance from Earth. From his 1929 data, Hubble derived a value for this constant of approximately 500 kilometers per second per megaparsec, meaning that for every megaparsec of distance, which is equivalent to about 3.26 million light-years, the recession velocity increased by roughly 500 kilometers per second. This value, as we now know from nearly a century of subsequent observations and refinements, was considerably too large, with modern measurements placing the Hubble constant at approximately 70 kilometers per second per megaparsec, nearly 7 times smaller than Hubble's original estimate. The discrepancy arose from several sources of error in Hubble's distance measurements, including a failure to recognize that there were two distinct types of Cepheid variable stars with different luminosity relationships, confusion between the brightest individual stars and bright regions of ionized hydrogen gas in distant galaxies, and various calibration uncertainties that accumulated through his distance ladder methodology. None of this diminishes the significance of his discovery, for what mattered was not the precise numerical value of the constant, but rather the recognition that such a constant relationship existed at all, that the universe exhibited this remarkable pattern of recession velocities increasing in direct proportion to distance. What is perhaps most striking about Hubble's 1929 paper is its brevity and its careful, almost tentative language. In just 2 pages, Hubble presented his data, described his methods, and noted the apparent linear relationship, but he refrained from drawing the cosmological conclusion that this relationship implied an expanding universe in which space itself was stretching and carrying the galaxies along with it. He spoke of the velocities as apparent velocities, hedging against the interpretation that these spectral shifts necessarily represented true physical motion through space, and he referred to the relationship as a possible correlation worthy of further investigation rather than as a definitive law of nature. This caution may have reflected Hubble's temperament as an observer who preferred to let the data speak without overreaching into theoretical interpretation, or it may have indicated genuine uncertainty about how to understand the implications of his findings, for the theoretical framework that would make sense of an expanding universe was still being developed by physicists and mathematicians working from rather different starting points. The story becomes more complex and more interesting from the perspective of how science actually unfolds, when we consider that 2 years before Hubble's paper appeared, A Belgian physicist and Catholic priest named Georges Lemaitre had published a remarkable paper that contained not only a similar velocity-distance relationship derived from observational data, but also a complete theoretical framework that explained why such a relationship should exist. Lemaitre had been trained in both physics and mathematics, and he understood the implications of Einstein's general theory of relativity for cosmology, recognizing that the equations permitted solutions in which space itself could expand or contract over time. In his 1927 paper, Lemaitre derived a model of an expanding universe directly from Einstein's field equations, calculated the expected relationship between galaxy distances and recession velocities, and then compared his theoretical prediction with the available observational data, finding good agreement between theory and observation. Lemaitre's paper, however, was published in the Annales de la Société Scientifique de Bruxelles, a respected but relatively obscure Belgian scientific journal, and it was written in French, which limited its accessibility to the predominantly English-speaking astronomical community that was making the crucial observations at observatories in California and elsewhere. The journal had a small circulation, and copies did not routinely make their way to the desks of astronomers at institutions like Mount Wilson, so Lemaitre's work remained largely unknown in the wider astronomical world for several years after its publication. Lemaitre himself was a modest man who did not aggressively promote his work, and the combination of an obscure publication venue, a language barrier, and the author's unassuming nature meant that his profound contribution went largely unnoticed at precisely the moment when Hubble was preparing to publish his own observational findings. The question of whether Hubble was aware of Lemaitre's work when he wrote his 1929 paper has been a matter of historical debate and some controversy. There is no direct evidence that Hubble had read Lemaitre's paper before publishing his own, and the two works are quite different in character, with Lemaitre's being a theoretical investigation that used observational data to support a cosmological model, while Hubble's was an observational report that carefully avoided cosmological interpretation. Some historians have argued that the astronomical community was small enough that word of Lemaitre's work might have reached Hubble through informal channels, perhaps through conversations at meetings or correspondence with colleagues who had read the Belgian journal, but no definitive evidence has emerged to support this possibility, and Hubble himself never acknowledged any awareness of Lemaitre's prior work. In 1931, Lemaitre's paper was translated into English and published in the monthly notices of the Royal Astronomical Society, finally bringing his work to the attention of the broader astronomical community, though by this time Hubble's name had already become firmly associated with the velocity-distance relationship in the minds of most astronomers. Curiously, the English translation omitted the section of Lemaitre's original paper in which he had derived a numerical value for the expansion rate from observational data, a value quite close to what Hubble would later publish. For many years, it was suspected that perhaps Hubble or someone acting on his behalf had arranged for this deletion to minimize the appearance of Lemaitre's priority, but a careful historical investigation completed in 2011 revealed that Lemaitre himself had made the decision to omit this section from the translation, apparently feeling that the data had been superseded by Hubble's more extensive and more accurate observations, and that there was no longer any point in reproducing his earlier, cruder estimate. Also in 1931, Hubble published a more comprehensive paper in collaboration with Milton Humason, who had risen from being a mule driver hauling equipment up Mount Wilson to become one of the most skilled observational astronomers of his generation. The Hubble and Humason paper extended the velocity-distance relationship to much greater distances than the original 1929 work, incorporating observations of galaxies whose recession velocities reached as high as 20,000 kilometers per second, far beyond anything in the earlier sample. This extended dataset confirmed that the linear relationship between velocity and distance continued to hold at these greater distances, strengthening the case that this was a genuine cosmic phenomenon rather than a statistical fluke or a local peculiarity of our neighborhood of space. With each passing year and each new observation, the reality of the velocity-distance relationship became more firmly established, and it became increasingly difficult to interpret it as anything other than evidence of a universe in which space itself was expanding. The recognition of Lemaitre's contribution came slowly and incompletely for many decades, with the velocity-distance relationship being almost universally referred to as Hubble's law throughout the 20th century, despite growing awareness among historians of science that Lemaitre had in some important senses gotten there first. The situation began to change in the early 21st century as a more complete historical picture emerged, and in 2018 the International Astronomical Union, the body responsible for official astronomical nomenclature, held a vote on whether to rename the relationship to acknowledge Lemaitre's contribution. The membership voted in favor of the change, and the relationship is now officially known as the Hubble-Lemaitre law, a name that recognizes both the Belgian priest who first derived the theoretical relationship and used observational data to estimate its value, and the American astronomer who provided the definitive observational confirmation that established the expanding universe as an empirical fact rather than a theoretical speculation. The story of how credit is assigned in science is rarely simple. 4 discoveries often emerge from the contributions of many individuals working in different places and approaching problems from different angles, and the person whose name becomes attached to a finding is not always the one who first had the key insight or gathered the crucial evidence. Slipher measured the velocities that made Hubble's analysis possible. Lemaitre derived the theoretical framework and recognized the cosmological significance of the velocity-distance relationship, and Hubble provided the definitive observational evidence that convinced the world. Each contribution was essential, and the Hubble-Lemaitre law, as it is now known, stands as a monument to their collective efforts, a simple linear relationship that opened a window onto the larger scales of space and time and revealed a universe far stranger and more dynamic than anyone had imagined. And so we come now to a rather remarkable figure in this story, a man who held 2 vocations that many of his contemporaries believed to be fundamentally incompatible, and yet he pursued both with quiet dedication and intellectual honesty throughout his long career. Georges Henri Joseph Edouard Lemaitre was born in the Belgian city of Charleroi in the year 1894, and from an early age he demonstrated both a profound religious faith and an equally profound curiosity about the physical workings of the natural world. He would eventually become an ordained Catholic priest, a canon of the Church, and at the same time one of the most original and important cosmologists of the 20th century. A combination that caused no small amount of confusion and occasionally suspicion among his scientific colleagues, though Lemaitre himself never seemed to find any contradiction in these parallel commitments. His early education was interrupted, as so many young lives were interrupted, by the First World War, during which Lemaitre served as an artillery officer in the Belgian army and witnessed some of the most terrible fighting of that conflict. After the war ended, he returned to his studies with renewed purpose, completing degrees in mathematics and physics at the Catholic University of Louvain, and also undertaking his training for the priesthood, which he completed in 1923. He was ordained as a priest that same year, and from that point forward he was often addressed as Abbé Lemaitre, the title indicating his status as a member of the clergy, though in scientific circles he was simply known as Professor Lemaitre or, in later years, Monseigneur Lemaitre when the Church elevated his rank in recognition of his contributions to human knowledge. What distinguished Lemaitre from many of his contemporaries was not merely his dual vocation but also the breadth and depth of his scientific training, which took him to some of the most important centers of astronomical and mathematical research in the world during the 1920s. He first traveled to Cambridge in England, where he spent the year 1923 to 1924 working under the supervision of Arthur Eddington, the same Arthur Eddington who had confirmed Einstein's general theory of relativity through the solar eclipse observations of 1919, and who was at that time one of the most respected astrophysicists in Britain. Eddington recognized in the young Belgian priest an exceptional mathematical talent and a genuine feel for the physical meaning behind the equations, and he encouraged Lemaitre to pursue research into the cosmological implications of general relativity, a field that was still quite new and full of unresolved questions. From Cambridge, Lemaitre crossed the Atlantic Ocean to continue his studies in the United States, spending time at both the Harvard College Observatory and the Massachusetts Institute of Technology, where he completed a doctoral thesis under the supervision of Harlow Shapley. During his time in America, Lemaitre had the opportunity to meet with the astronomers who were then engaged in measuring the distances and velocities of the spiral nebulae, including Vesto Slipher, whose redshift measurements would prove so important to the developing picture of an expanding universe. Lemaitre learned about these observations firsthand, and he began to see how they might be connected to the theoretical models that emerged from Einstein's equations of general relativity. It was during this period of intense study and reflection that Lemaitre began to develop his own cosmological model, working through the mathematics of general relativity and arriving at conclusions that were both mathematically sound and physically startling. In 1927, he published a paper in an obscure Belgian scientific journal called the Annales de la Société Scientifique de Bruxelles, and in this paper he presented a model of the universe that was expanding, with the distances between galaxies increasing over time according to a precise mathematical relationship. He derived from Einstein's field equations the theoretical basis for this expansion, and he also used the available observational data on nebular redshifts and distances to calculate a numerical value for the rate at which the universe was expanding, a quantity that we now call the Hubble constant, though Lemaitre calculated it 2 years before Edwin Hubble published his own more famous analysis. The paper was written in French and published in a journal that few astronomers outside Belgium ever read, and as a result it attracted almost no attention at the time. Lemaitre sent a copy to Arthur Eddington, his former supervisor, but Eddington apparently did not read it carefully or did not appreciate its significance, and the paper languished in obscurity for several years while other scientists wrestled with the same questions without knowledge of Lemaitre's prior work. This was an unfortunate circumstance that would later require some correction when the scientific community finally became aware of what Lemaitre had accomplished. But in the meantime, the young priest returned to Belgium and took up a position at the Catholic University of Louvain, where he continued to develop his ideas about the large-scale structure and evolution of the cosmos. The situation changed rather dramatically in the year 1930, when Eddington finally recognized the importance of Lemaitre's work and began to bring it to the attention of the broader scientific community. Eddington had been troubled by the static models of the universe that were then standard, models that seemed to require a precarious balance between gravitational attraction and the repulsive effect of the cosmological constant. And when he revisited Lemaitre's paper, he realized that the Belgian priest had already solved the problem by allowing the universe to be genuinely dynamic, expanding outward from a denser past state into an ever more diffuse future. Eddington arranged for an English translation of Lemaitre's paper to be published in the monthly notices of the Royal Astronomical Society in 1931. And from that point forward, Lemaitre's contribution to cosmology began to receive the recognition it deserved. But Lemaitre was not content to stop with the observation that the universe is expanding. He wanted to understand what this expansion implied about the distant past, and he pursued this question with characteristic mathematical rigor and physical imagination. If the universe is currently expanding, he reasoned, then at earlier times it must have been smaller and denser, and if one traced this expansion backward in time far enough, one would eventually arrive at a state of extreme compression, a state in which all the matter and energy of the universe was concentrated into a volume of extraordinary density. In a series of papers and lectures beginning in 1931, Lemaitre proposed that the universe had originated from what he called the prime valatum, sometimes also referred to as the cosmic egg, a single quantum of immense energy from which the entire physical cosmos had emerged through a process of expansion and differentiation. This was a profoundly new idea, and Lemaitre described it in language that was both scientifically precise and poetically evocative. He spoke of the beginning of the world as a day without yesterday, a moment when time itself began along with space and matter, a singular origin that could not be preceded by any earlier state because there was no earlier state, no before, no prior emptiness waiting to be filled. The prime valatum was not an object sitting in pre-existing space, but rather the seed from which space and time themselves unfolded, and its explosion, if we may use that term loosely, was not an explosion into anything but rather an explosion of everything, the coming into being of the physical universe with all its subsequent complexity and structure. Lemaitre presented these ideas at a meeting of the British Association for the Advancement of Science held in London in May of 1931, and it was at this meeting that his cosmological vision first received wide public and professional attention. Arthur Eddington, who had by now become a strong advocate for Lemaitre's work, helped to arrange for the Belgian priest to address the assembled scientists, and the response was a mixture of fascination, skepticism, and, in some quarters, genuine discomfort. The notion that the universe had a definite beginning, a moment of creation from which all subsequent history flowed, struck many scientists as uncomfortably close to the creation narratives found in religious texts, and they worried that accepting such a cosmology would be tantamount to allowing religious doctrine to influence scientific theory. Albert Einstein himself was initially quite dismissive of Lemaitre's ideas, and when the two men met in Brussels in 1927, Einstein reportedly told Lemaitre that while his mathematics was entirely correct, his physical interpretation was abominable, or words to that effect. Einstein at that time still preferred a static universe and was reluctant to accept the radical implications of his own equations. But as the observational evidence for cosmic expansion accumulated over the following years, his resistance gradually softened. By 1933, when Einstein and Lemaitre both attended a series of lectures in California, Einstein had come to regard the expanding universe as a genuine possibility, and he publicly acknowledged the importance of Lemaitre's contributions, reportedly standing and applauding after one of the Belgian priest's presentations and declaring it the most beautiful and satisfying explanation of creation he had ever heard. The resistance from other scientists was slower to fade, and it took various forms depending on the individual concerned. Some objected on purely scientific grounds, arguing that the evidence was not yet sufficient to support such a dramatic conclusion, or that alternative explanations for the observed redshifts might eventually be found. Others were more openly troubled by the philosophical and theological implications of a universe with a definite beginning, feeling that such a cosmology opened the door to religious explanations that had no place in scientific discourse. This discomfort would persist for many years and would eventually give rise to competing cosmological theories, most notably the steady-state theory proposed in the late 1940s by Hermann Bondi, Thomas Gold, and Fred Hoyle, which held that the universe had no beginning and no end but existed eternally in a state of continuous creation, with new matter appearing spontaneously to fill the voids left by cosmic expansion. It was Fred Hoyle, in fact, who coined the term that would eventually become the standard name for Lemaitre's cosmological picture, though he intended it as a term of derision rather than description. In a BBC radio broadcast in 1949, Hoyle referred dismissively to the idea of the universe originating in a single explosive moment as the Big Bang Theory, contrasting it unfavorably with his own preferred steady-state model, and the name stuck despite its pejorative origins, becoming the common term for the expanding universe cosmology that Lemaitre had pioneered decades earlier. Lemaitre himself never used this term and reportedly found it somewhat vulgar, preferring his own more dignified language of the primeval atom and the cosmic egg. Throughout all of this controversy, Lemaitre maintained a careful and deliberate separation between his scientific work and his religious beliefs, insisting that his cosmology was based entirely on the mathematics of general relativity and the evidence of astronomical observation, not on any theological premise or scriptural interpretation. He was sometimes pressed by journalists and colleagues to explain how his faith influenced his science, or how his science affected his faith, and he consistently declined to conflate the two, arguing that they addressed different questions and operated in different domains. The Bible, he said, was not a textbook of astronomy, and one should not look to it for information about the physical structure of the universe, just as one should not look to physics for answers to questions of ultimate meaning and purpose. This careful distinction was put to an unexpected test in 1951, when Pope Pius XII gave an address to the Pontifical Academy of Sciences in which he enthusiastically endorsed the Big Bang cosmology as scientific confirmation of the creation account in the Book of Genesis, declaring that modern science had confirmed the contingency of the universe and the existence of a creator. Lemaitre was deeply uncomfortable with this papal endorsement, feeling that it blurred the very boundary between science and theology that he had worked so hard to maintain, and he quietly lobbied Vatican officials to persuade the Pope to refrain from making such statements in the future. The universe might indeed have had a beginning, Lemaitre believed, but this was a scientific conclusion reached through scientific methods, and it should not be appropriated as evidence for religious doctrine, however tempting such an appropriation might be for those who wished to harmonize faith and reason. Lemaitre continued his scientific work for many more years, refining his cosmological models and contributing to other areas of mathematics and physics, and he lived long enough to see his early insights vindicated by new observational evidence, including the discovery of the cosmic microwave background radiation in 1965, which provided strong support for the idea that the universe had once existed in a hot, dense state. He died in 1966, just a few weeks after learning of this discovery, having spent his life quietly insisting that the universe could be understood through careful observation and rigorous mathematics, and that such understanding was perfectly compatible with, though entirely separate from, a life of faith and prayer. And so we come now to the quiet unraveling of a conviction, the gentle loosening of a position that Albert Einstein had held for more than a decade. And we find ourselves in the early 1930s, when the evidence for an expanding universe had grown so substantial, so carefully documented, so thoroughly confirmed by multiple observers using the finest instruments available, that even the most reluctant minds were beginning to accept what the cosmos seemed to be telling them. And Einstein, for all his towering intellect and his profound contributions to our understanding of space and time and gravity, was among those who had resisted this particular truth, having introduced his cosmological constant precisely to avoid the implication that the universe might be anything other than eternal and unchanging. And now, as we shall see, he would come to regard this intervention as a profound mistake, though the full story of his acceptance unfolds gradually, with visits and conversations and papers and letters, all proceeding at the measured pace that suits our purposes here as we settle into this account of how one of history's greatest physicists came to terms with an expanding cosmos. The year 1930 brought Einstein to California, to the Golden Hills and the clear mountain air of Pasadena, where the California Institute of Technology had invited him to spend time as a visiting scholar. And this visit would prove particularly significant because it brought him into direct contact with Edwin Hubble, the man whose observations had done more than anyone else's to establish the reality of cosmic expansion. And the two men met at the Mount Wilson Observatory, that remarkable facility perched above the Los Angeles basin where the 100-inch Hooker telescope, then the largest in the world, had been gathering light from distant galaxies and revealing their secrets to patient observers. And here, in the dome of that great instrument, Hubble showed Einstein the evidence firsthand: the photographic plates, the spectroscopic data, the careful measurements of distances and velocities that, when plotted together, revealed that unmistakable relationship between how far away a galaxy lies and how quickly it appears to be receding from us. One can imagine the scene with a certain tender appreciation for its historical weight. Einstein peering at the data that contradicted his long-held assumptions, Hubble explaining the methodology with the careful precision of an observer who had spent countless nights at the eyepiece, the mountain air cool and thin at that altitude, the great telescope standing ready for another night of cosmic exploration. And among those present was Elsa Einstein, Albert's wife, who accompanied him on many of his travels and who possessed a warm wit that she deployed on this occasion when reporters asked her about the significance of what her husband was seeing. And she remarked, with what we might call affectionate irreverence, that her husband too had worked out the structure of the universe, though he had done so on the back of an old envelope, a comment that gently punctured any excessive solemnity, while also acknowledging the profound theoretical work that Einstein had contributed to cosmology, even if his specific prediction of a static universe was now being contradicted by these very observations. The visit to Mount Wilson was not merely ceremonial or social, but represented a genuine engagement with the evidence. And Einstein, whatever his previous resistance to the idea of expansion, was never one to ignore empirical facts when they were presented clearly and convincingly. And the data that Hubble showed him was indeed convincing, built up over years of painstaking observation, checked and rechecked, refined and extended, until the relationship between distance and recession velocity stood as one of the most robust findings in all of astronomy. And so Einstein found himself in the position of having to revise his thinking, to acknowledge that the universe was not the static eternal structure he had assumed, but rather a dynamic evolving system, expanding outward from some earlier more compressed state. In January of 1931, a gathering took place in Pasadena that brought together some of the most distinguished minds then working on questions of cosmology and relativity, and among those present were Einstein and Hubble, along with other luminaries who had contributed to the unfolding understanding of the universe's structure. And this meeting represented a kind of informal summit at which the implications of the new observations could be discussed and debated, theories compared with data, mathematical frameworks tested against empirical findings. And while we do not have detailed transcripts of all that was said during these conversations, we know that Einstein emerged from this period with a fundamentally altered view of the cosmos, ready to abandon the modification he had made to his equations more than a decade earlier. Later that year, in 1931, Einstein published a paper that marked his formal acceptance of the expanding universe and his abandonment of the cosmological constant, the modification he had introduced in 1917 to keep his equations from predicting cosmic expansion. And in this paper he acknowledged that the evidence now strongly supported a universe that was indeed growing larger over time, that the static model he had preferred was no longer tenable in the face of Hubble's observations, and that the cosmological constant he had introduced served no useful purpose and could be removed from the equations without loss. Indeed with positive benefit, since its removal allowed the theory to align with what astronomers were actually observing when they pointed their telescopes at distant galaxies and measured the shifting of their spectral lines. The question of whether Einstein actually used the phrase that has become so famous, calling the cosmological constant his greatest blunder, or words to that effect, is one that historians have examined with considerable care. And the evidence suggests that this particular characterization comes to us primarily through the physicist George Gamow, who reported that Einstein had made such a remark in conversation. And Gamow was indeed someone who knew Einstein and worked on related cosmological questions. But we should note that no written record of Einstein using these exact words has been found in his papers or correspondence. And so while the phrase captures something true about Einstein's regret over the episode, we cannot be entirely certain that he expressed this regret in quite these dramatic terms, though it is equally possible that he did say something along these lines in a casual conversation that Gamow accurately remembered and later reported. What we can say with more confidence is that Einstein's correspondence from this period and afterward does express genuine regret about the cosmological constant episode, and particularly about his initial dismissal of the theoretical work done by others who had predicted expansion before the observational evidence became overwhelming. And here we must mention Einstein's acknowledgement of the priority of Alexander Friedmann and Georges Lemaitre, both of whom had developed theoretical models predicting an expanding universe years before Hubble's observations made such models empirically necessary. And Einstein had initially been dismissive of this theoretical work, having written that note questioning Friedmann's mathematics, which turned out to be entirely correct, and having apparently overlooked or undervalued Lemaitre's similar conclusions when they were first presented. In his later correspondence, Einstein acknowledged that Friedmann and Lemaitre deserved credit for having arrived at the theoretical prediction of expansion through their mathematical analysis of the general relativistic equations, and that his own resistance to their conclusions had been based not on any flaw in their reasoning, but on his philosophical preference for a static universe, a preference that the actual universe had no obligation to satisfy. And this acknowledgement represents a kind of intellectual generosity that we might find admirable, the willingness to recognize that others had seen more clearly and further than oneself, even when one happens to be Albert Einstein. The year 1932 brought another significant paper, this one written jointly by Einstein and Willem de Sitter, the Dutch astronomer whose own cosmological solutions had contributed so much to the theoretical understanding of relativistic universes, and together they proposed what became known as the Einstein-de Sitter model, a cosmological model that assumed an expanding universe with zero cosmological constant, and with a specific relationship between the density of matter and the rate of expansion. And this model became for many decades the standard reference point in cosmology, a kind of baseline against which other models could be compared, simple and elegant in its assumptions even if the actual universe might turn out to be somewhat more complicated. The Einstein-de Sitter paper represented Einstein's complete acceptance of cosmic expansion and his thorough rejection of the cosmological constant, and for the remaining decades of his life and for many years afterward, most cosmologists followed his lead in treating the cosmological constant as an unnecessary complication, a historical curiosity, a modification that had been introduced to solve a problem that turned out not to exist and that could therefore be safely discarded. And this view prevailed for most of the 20th century. with the expanding universe model becoming the standard framework for understanding cosmic evolution, tracing back through time to an early hot dense state and forward to an ever more spread out and cooled future. But here we encounter one of those gentle ironies that make the history of science so interesting to contemplate in these quiet hours. For the cosmological constant that Einstein rejected, the modification he may or may not have called his greatest blunder, did not remain discarded forever, and in 1998, observations of distant supernovae revealed something unexpected and remarkable, namely that the expansion of the universe is not merely continuing but actually accelerating, speeding up over time rather than slowing down as one might expect if gravity were the only force at work. And this accelerating expansion requires some explanation, some additional factor that pushes space apart ever faster. And the explanation that cosmologists have adopted involves something called dark energy, a mysterious component of the universe that behaves in a manner very similar to what Einstein's cosmological constant would produce. And so the cosmological constant, or something very much like it, has returned to our equations, reintroduced not as a philosophical preference or a mathematical convenience but as an empirical necessity, required to explain what we actually observe when we study the expansion history of the cosmos. And this means that Einstein's original modification, the one he introduced and then rejected, may not have been a blunder at all, or at least not a simple blunder, but rather an insight that was in some sense correct, even if Einstein himself introduced it for the wrong reasons and then abandoned it when those reasons proved mistaken. And the universe, in its characteristic indifference to human expectations, has turned out to require something like the cosmological constant after all. There is something deeply fitting about this turn of events, something that invites us to reflect on the provisional nature of scientific knowledge and the way that ideas once discarded can return in new forms to explain new phenomena. And Einstein, had he lived to see the discovery of dark energy and the revival of the cosmological constant, might have found the situation both amusing and instructive, a reminder that the universe always has more to teach us and that our theories, however elegant, must ultimately bow to what observations reveal. And this was a lesson that Einstein himself learned in the early 1930s when he accepted the expanding universe and acknowledged the priority of those who had predicted it before him. As we rest here with this thought, with the image of Einstein at Mount Wilson examining the evidence that would change his view of the cosmos, with the letters he wrote acknowledging his errors and crediting others with theoretical priority, with the papers he published abandoning his cosmological constant and embracing the dynamic expanding universe, we can appreciate that even the greatest minds must sometimes revise their positions, must acknowledge when they have been wrong, must accept that the universe operates according to its own rules rather than our preferences. And there is something reassuring in this, something that tells us that science works precisely because it allows for such revisions, such acknowledgements, such humble acceptance of empirical facts. And with that comforting thought we continue gently forward, or perhaps simply rest here for a moment, breathing slowly, letting the story of cosmic expansion settle into the quiet spaces of the mind as sleep approaches and the day's concerns fade into the vast expanding darkness. In order to understand how astronomers came to discover that the universe was expanding, it is helpful first to appreciate the tools and techniques they relied upon, the patient methods by which they gathered their evidence, and the careful ways they learned to read the distant light of stars. These methods may seem, at first, rather technical, and perhaps even a little dry, but there is something restful in their precision, something calming in the knowledge that great discoveries were built upon countless small, methodical steps, each one carefully recorded and verified before the next could be taken. The foundation of nearly all astronomical observation during this period was the photographic plate, a seemingly simple object that nevertheless transformed the study of the heavens. These plates were typically made of glass, quite thick and heavy compared to the flexible film that would come later, and they were coated with a thin layer of emulsion containing silver bromide crystals suspended in gelatin. When light struck these crystals, it caused a subtle chemical change, invisible at first, which could later be developed using various chemical baths to reveal a permanent image of whatever had been photographed. The glass provided a stable, flat surface that would not warp or stretch over time, which was essential for making precise measurements of star positions that might need to be compared across many years or even decades. The sensitivity of these photographic emulsions was, by modern standards, quite limited, and this limitation shaped the entire practice of astronomical photography. Where a modern digital camera might capture a faint galaxy in seconds, the photographic plates of the early 20th century required exposures lasting many minutes, or even several hours, to record the dim light of distant celestial objects. During these long exposures, the telescope had to track the apparent motion of the stars across the sky with extraordinary precision, compensating for the rotation of the Earth, and any slight vibration or drift would blur the resulting image and render it useless for careful measurement. Astronomers would sometimes sit for hours in the cold darkness of their observatory domes, monitoring the tracking mechanisms and making tiny corrections by hand, all for a single photograph that might or might not yield useful data. Despite these difficulties, the photographic plate offered something invaluable, which was permanence. Unlike a visual observation made through an eyepiece and then recorded in a notebook from memory, a photographic plate captured the actual light that had fallen upon it, preserving that information in a form that could be examined again and again, measured with rulers and microscopes, compared with other plates taken at different times, and stored in archives for future generations to study. The great astronomical observatories accumulated vast collections of these plates, hundreds of thousands of them eventually, each one a frozen moment of the night sky that could be revisited whenever new questions arose or new methods of analysis became available. To extract the deepest secrets from starlight, however, required more than simply photographing the positions and brightnesses of stars. It required spectroscopy, the technique of spreading light out into its component wavelengths, much as a prism spreads a beam of sunlight into the familiar colors of the rainbow. In astronomical spectroscopy, the light gathered by a telescope was directed through a prism, or in later and more refined instruments through a diffraction grating, which achieved the same spreading effect through the interference of light waves passing through many closely spaced parallel lines. The resulting spectrum could then be photographed, producing a long strip of image showing how the intensity of the light varied across different wavelengths, from the deep red at one end through orange, yellow, green, and blue, to the violet at the other. What made spectroscopy so powerful was the presence within these spectra of dark or bright lines at very specific wavelengths, lines that corresponded to the absorption or emission of light by particular chemical elements. Each element, whether hydrogen, helium, iron, calcium, or any other, produced its own unique pattern of lines, a kind of fingerprint that could be recognized wherever it appeared. By examining the spectrum of a star and identifying which lines were present, astronomers could determine what elements existed in the outer layers of that star, even though the star itself was unimaginably far away and would never be visited by any human being. This was a remarkable thing, really, to sit in an observatory on Earth and to know with confidence that a particular star contained iron, or that its atmosphere was rich in hydrogen, simply by studying the pattern of dark lines crossing its spectrum. Even more useful for the study of the expanding universe was the way these spectral lines could reveal motion. When a source of light is moving toward an observer, the wavelengths of its light are compressed slightly, shifting the entire spectrum toward the blue end. And when the source is moving away, the wavelengths are stretched, shifting the spectrum toward the red. This is the Doppler effect, the same phenomenon that causes the pitch of a passing train's whistle to drop as it moves away from you, and it applies to light just as it applies to sound. By measuring how much the spectral lines of a star or galaxy had shifted from their normal positions, astronomers could calculate how fast that object was moving toward or away from the Earth, a quantity known as its radial velocity. This technique would prove absolutely essential when the time came to measure the motions of distant galaxies and to detect the systematic recession that indicated the expansion of the universe. Knowing the velocities of celestial objects was only half of what was needed. However, to understand the true nature of the cosmos, astronomers also needed to know distances, and measuring distances to objects beyond our solar system was, and in many ways still is, one of the most challenging problems in all of astronomy. The method that proved most valuable during this period was based on a particular type of star known as a Cepheid variable, named after the constellation Cepheus, where the first well-studied example was found. These stars pulsate in a regular, rhythmic way, brightening and dimming over periods ranging from a few days to several weeks, and this pulsation is driven by physical processes in the star's outer layers that cause it to expand and contract in a repeating cycle. The crucial discovery, made through the patient analysis of many photographic plates, was that the period of a Cepheid's pulsation was directly related to its intrinsic luminosity, which is to say, to how much light it actually emitted. A Cepheid that took longer to complete its cycle of brightening and dimming was genuinely more luminous than one with a shorter period. This relationship, known as the period-luminosity relation, meant that by measuring how long a Cepheid took to go through its pulsation cycle, an astronomer could determine how bright that star truly was. Comparing this intrinsic brightness, or absolute magnitude, with how bright the star appeared in the sky, its apparent magnitude, allowed the astronomer to calculate how far away the star must be. The mathematics involved was straightforward, based on the principle that light spreads out as it travels through space, growing dimmer with distance according to a simple inverse square law. The difference between apparent and absolute magnitude, called the distance modulus, could be converted directly into a distance in light years or parsecs. This method required, of course, the ability to recognize Cepheid variables in the first place, and to measure their periods and apparent brightnesses with sufficient accuracy. Here the photographic plate proved indispensable, because by taking many photographs of the same region of the sky over weeks or months, and then comparing them carefully, astronomers could identify stars that changed in brightness and trace out the shape of their light curves, the graphs showing how their brightness varied over time. An instrument called a blink comparator was particularly useful for this work. It held two photographic plates taken at different times and allowed the observer to switch rapidly between viewing one and viewing the other. Any star that had changed in brightness or position would seem to blink or jump as the view alternated, making it stand out from the thousands of unchanging stars around it. The measurement of star brightnesses on photographic plates, a technique known as photographic photometry, was itself a careful and somewhat tedious process. The darkness of a star's image on the plate depended on how much light had fallen upon that spot during the exposure, but the relationship was not perfectly straightforward, and various corrections had to be applied for the characteristics of the particular emulsion, the length of the exposure, and other factors. Standard reference stars of known brightness were photographed alongside the objects being studied, allowing their images to serve as comparison points, and specialized measuring instruments were used to determine just how dark each stellar image was, translating that measurement into a magnitude value. All of this work was complicated by the interference of Earth's atmosphere, that thin shell of air that lies between every ground-based telescope and the stars it observes. The atmosphere bends and distorts light, causing stars to twinkle and smearing their images into small blurry disks rather than the perfect points they would be if viewed from space. The amount of this distortion, called seeing, varies from night to night and even from moment to moment, depending on temperature, wind, humidity, and countless other factors. Even on the clearest nights, the atmosphere absorbs some of the starlight passing through it, particularly at certain wavelengths, and astronomers had to account for this absorption when making their measurements. Observatories were built on mountaintops partly to rise above the densest layers of atmosphere, and astronomers learned to recognize and wait for the nights of best seeing, when the air was calm and steady and the stars shone as still and sharp as possible. Light pollution, too, was becoming a concern even in this era, though it was nothing compared to what it would become later in the 20th century. The glow of city lights scattered by the atmosphere created a diffuse brightness in the night sky that could wash out the faintest stars and make it harder to photograph dim objects. Observatories that had once enjoyed dark skies found themselves increasingly troubled by the growth of nearby towns and cities, and the search for darker sites drove the construction of new facilities in more remote locations. Behind all of this technical work, enabling and supporting the discoveries that would transform our understanding of the universe, was a group of remarkable individuals whose contributions were essential but who received far less recognition than they deserved. At the Harvard College Observatory, a team of women known informally as the Harvard Computers spent long hours examining photographic plates, measuring star positions and brightnesses, classifying spectra, and recording their findings in meticulous catalogues. This work was considered suitable for women at the time precisely because it was seen as tedious and clerical, requiring patience and attention to detail rather than the creative insights supposedly reserved for men. The women were paid wages significantly lower than their male colleagues, often less than half as much, and they were not permitted to operate the observatory's telescopes themselves, being relegated instead to the analysis of data that others had collected. Yet from this position of institutional disadvantage came discoveries of the greatest importance. Henrietta Leavitt, working through thousands of photographic plates of the Small Magellanic Cloud, identified the period-luminosity relationship in Cepheid variables that would become the essential tool for measuring cosmic distances. Her finding, published first as a brief note in 1908 and then more fully in 1912, was credited at the time to the observatory's director, Edward Pickering, whose name appeared on the paper even though the work was entirely Leavitt's own. Annie Jump Cannon developed the stellar classification system that organized stars by their spectral characteristics into a sequence that is still used today, examining and classifying the spectra of several 100,000 stars over the course of her career. Cecilia Panga-Poshkin, whose doctoral thesis of 1925 demonstrated that stars were composed primarily of hydrogen and helium rather than the heavier elements common on Earth, was told by a senior astronomer that her conclusion was almost certainly wrong, and she was persuaded to downplay her findings, only to see the same conclusion accepted when a male astronomer published it 4 years later. These women and their colleagues worked in a system that systematically undervalued their contributions, yet without their painstaking analysis of photographic plates, their careful measurements and classifications, the great cosmological discoveries of the early 20th century would not have been possible. They represent a quieter kind of scientific heroism, one measured not in dramatic moments of insight but in the steady accumulation of accurate data over many years, the building of foundations upon which others would construct more visible achievements. And so the tools and techniques of early 20th century astronomy, the photographic plates and spectroscopes, the blink comparators and photometric measurements, the period-luminosity relation and the tireless work of the Harvard computers, came together to make possible a new understanding of the cosmos. These methods were slow, demanding, and often frustrating, requiring patience that might stretch across years or even decades, but they provided a kind of evidence that could be trusted, checked, and built upon. In the sections that follow, we will see how these tools were applied to the great questions of the time, revealing a universe far larger and far stranger than anyone had imagined, a universe that was not static and eternal but dynamic and evolving, expanding outward into an endless night. By the year 1932, a person standing on any street corner in London or New York or Sydney, looking up at the night sky, would have been gazing upon the same scattered points of light that their grandparents had observed, the same constellations wheeling slowly overhead, the same pale smear of the Milky Way arching from horizon to horizon on clear evenings away from city lights. The sky itself had not changed in any perceptible way, and yet everything known about that sky, everything understood about those seemingly fixed and eternal points of light, had been utterly transformed in the span of barely 2 decades, a period shorter than the time it takes for a child to grow to adulthood, shorter than the typical span of a single scientific career, and yet long enough for humanity's entire conception of the cosmos to shift from one understanding to something almost unrecognizably different. In 1912, the universe had been, for most astronomers and certainly for most members of the general public, a rather comprehensible place, finite in extent and essentially unchanging in its fundamental nature, consisting primarily of our own Milky Way system with its hundreds of millions of stars, surrounded perhaps by empty space or perhaps by other matter of uncertain character, but in any case representing a cosmos that could be visualized without too much difficulty, a cosmos that did not strain the imagination beyond comfortable limits. The spiral nebulae were objects of curiosity and debate, their nature uncertain, their distances unknown, their relationship to our own stellar system a matter for speculation rather than settled knowledge. The idea that the universe might be expanding, that space itself might be stretching and carrying galaxies apart from one another, would have struck most people, scientific or otherwise, as belonging more properly to the realm of imaginative fiction than to serious astronomical consideration. And yet, by 1932, this comfortable and comprehensible universe had been replaced by something vastly larger and stranger, a cosmos containing not one but billions of separate galaxies, each one a great island universe in its own right, each containing its own billions of stars, and all of these countless island universes rushing away from one another at velocities that increased with distance, the most remote objects receding at speeds that seemed almost impossible to credit, carrying them away at thousands of miles per second, their light reddened by the stretching of space itself, their faintness a measure of distances so vast that light from their stars had been traveling toward Earth for millions upon millions of years. The transformation in understanding was so complete, so fundamental, that it represented perhaps the most profound shift in humanity's cosmic perspective since Copernicus had displaced the Earth from the center of creation nearly 4 centuries earlier. The general public became aware of these discoveries gradually, through newspaper reports that appeared with increasing frequency as the 1920s progressed into the 1930s. And among the publications that covered these astronomical developments with particular attention was the New York Times, which had established itself as a paper of record for scientific news and which reported regularly on the discoveries emerging from Mount Wilson Observatory and from other centers of astronomical research around the world. The reports tended toward measured language, as befitted discussions of matters that many readers would find difficult to comprehend fully. And yet, even in measured language, the implications of what was being discovered carried a certain weight that thoughtful readers could not help but notice. When Edwin Hubble's work establishing the distances to external galaxies became widely known, and when his subsequent discovery of the velocity-distance relationship was announced, the newspapers conveyed to their readers the essential facts, explaining in terms accessible to general audiences that the universe appeared to be vastly larger than previously imagined, and that it appeared to be expanding in all directions, the galaxies moving apart like raisins in a rising loaf of bread, to use an analogy that became popular in explanatory accounts of the period. The reading public responded with a mixture of fascination and something harder to name, a kind of existential unease perhaps, a sense that the ground beneath human certainty had shifted in ways that would take time to fully appreciate. This unease found expression in philosophical reflections that appeared in books and essays throughout this period, and among the thinkers who contemplated the implications of the new cosmology was the philosopher and mathematician Bertrand Russell, who wrote with characteristic clarity about what he perceived as humanity's diminished significance in the vast and impersonal cosmos that science was revealing. Russell observed that the universe as now understood offered no special place for human concerns, no indication that the cosmos had been arranged for human benefit or with human meaning in mind, and he suggested that honest contemplation of our situation required a kind of stoic courage, an acceptance of cosmic insignificance that might ultimately prove liberating rather than crushing. His reflections represented one strand of philosophical response to the new cosmology, a strand that emphasized the apparent indifference of the universe to human hopes and fears, and that called for a mature acceptance of this indifference rather than a retreat into comforting but unwarranted beliefs. Religious thinkers responded to the new cosmology in various ways, some finding in the vastness of creation additional cause for wonder at divine power and wisdom, others wrestling with questions about the relationship between scriptural accounts of creation and the picture of the universe that was emerging from astronomical observation. The idea that the universe might have a finite age, that it might have begun at some definite moment in the past when all matter was compressed together, struck some religious commentators as unexpectedly consonant with traditional ideas about creation, while others remained cautious about reading theological significance into scientific findings that might themselves be revised or superseded as knowledge advanced. The debates were conducted with varying degrees of sophistication and mutual understanding, and they continue in various forms to this day, as thoughtful people attempt to reconcile scientific descriptions of the physical world with frameworks of meaning and value that speak to different human needs. Not all astronomers accepted the expanding universe interpretation without reservation, and it should be noted that by 1932 there remained a current of scientific skepticism about whether the observed redshifts of distant galaxies truly indicated recessional velocities, or whether some other physical mechanism might be responsible for the shifting of spectral lines toward longer wavelengths. Among the alternative explanations that were proposed and discussed was the idea that light might lose energy during its long journey through space, becoming progressively redder as it traveled across the vast distances between galaxies, not because the galaxies were moving away, but simply as a natural consequence of the passage of light through intergalactic space over millions of years. This proposal, which came to be known informally as the tired light hypothesis, was taken seriously enough to warrant careful consideration, and various versions of it were developed by astronomers who remained unconvinced that the universe was truly expanding. The tired light alternatives faced difficulties of their own, including the problem of explaining by what physical mechanism light would lose energy in the vacuum of space without also blurring or otherwise distorting the images of distant galaxies in ways that were not observed. And over time, the evidence accumulated in favor of the expansion interpretation rather than these alternative explanations. But in 1932, the matter was not yet entirely settled in the minds of all astronomers, and the debates continued in observatory offices and in the pages of scientific journals, as is proper and healthy in any field of inquiry where certainty has not yet been established beyond reasonable doubt. The International Astronomical Union, the professional body that coordinates matters of astronomical nomenclature and standardization across national boundaries, took note of the developing understanding of external galaxies, and at its meeting in 1928 formally adopted the term galaxy to describe these great stellar systems, distinguishing them from true nebulae, which were clouds of gas and dust within our own Milky Way rather than separate island universes of stars at vast distances beyond. This terminological clarification reflected the growing consensus among professional astronomers that the spiral nebulae and their cousins were indeed independent galaxies comparable to our own, and the adoption of standard terminology helped to reduce confusion in both technical discussions and popular accounts of astronomical matters. The state of cosmological knowledge in 1932 might be summarized as follows, though of course any summary necessarily omits much that contemporary astronomers would have considered important. The expansion of the universe appeared to be confirmed, with the velocity-distance relationship established by Hubble's work providing strong evidence that galaxies were indeed receding from one another in the manner predicted by relativistic cosmological models. The universe was understood to contain vast numbers of galaxies, distributed through space in a roughly uniform manner when viewed on sufficiently large scales, and the distances to these galaxies were measured in millions of light-years, with the most remote objects detected lying at distances of perhaps 100 million light-years or more. And yet, alongside these remarkable advances in understanding, there remained puzzles and paradoxes that would occupy astronomers for years and decades to come. Perhaps the most troubling of these was the apparent age paradox, for when astronomers attempted to calculate how long ago the expansion had begun, running the cosmic clock backward to the moment when all matter would have been compressed together, they arrived at estimates suggesting that the universe was perhaps 2 billion years old, give or take a factor of uncertainty. This presented a serious difficulty, for by 1932 geologists had established through the analysis of radioactive decay in rocks that the Earth itself was at least 2 or 3 billion years old, and it seemed impossible that the Earth could be older than the universe that contained it. This paradox would not be resolved for another 2 decades, when revisions to the cosmic distance scale would show that Hubble's original estimates of galactic distances had been too small, and that the universe was in fact considerably older than the initial calculations had suggested. But in 1932 the paradox remained, a reminder that the emerging cosmological picture, however revolutionary, was not yet complete or fully consistent. Other mysteries were also beginning to emerge from careful astronomical observation. The Dutch astronomer Jan Oort, studying the motions of stars in the Milky Way, noticed that stars appeared to be moving under the gravitational influence of more matter than could be accounted for by the visible stars alone, suggesting that some form of invisible or dark matter might pervade our galaxy, contributing to its gravitational field without emitting or reflecting light in amounts sufficient for detection. This early suggestion of what would later become one of the central problems of modern cosmology, the nature and distribution of dark matter, was in 1932 still a tentative inference rather than an established fact, but it pointed toward future discoveries that would further complicate the emerging picture of the cosmos. Meanwhile, the American physicist Robert Millikan was pursuing studies of cosmic rays, those highly energetic particles that constantly bombard Earth's atmosphere from space, and he proposed that these rays might represent what he poetically described as the birth cries of atoms, the energetic signatures of matter being created somewhere in the depths of space. This interpretation would not survive later investigation, but it reflected the spirit of a time when fundamental questions about the origin and nature of matter seemed to be within reach of experimental resolution, and when the boundaries between astronomy and physics were becoming increasingly blurred as both disciplines converged on questions of cosmic significance. The transformation from the cozy and comprehensible Milky Way universe of 1912 to the vast and dynamic cosmos of 1932 was complete in its essential outlines, even if many details remained to be filled in and many puzzles remained to be solved. Humanity had learned that it inhabited a small planet orbiting an ordinary star in an ordinary galaxy, one among billions of similar galaxies scattered through an expanding universe of almost inconceivable vastness. The cosmos had become larger, stranger, and in some ways less hospitable to human hopes for significance, and yet the very fact that human minds could comprehend this vastness, could trace the motions of distant galaxies and calculate the age of the expanding universe, might be taken as a kind of significance in itself, a demonstration of the remarkable capacity of the human intellect to extend beyond its immediate circumstances and grasp something of the nature of the whole. And with this transformed understanding, the astronomers and physicists of 1932 looked forward to continued investigation, confident that more would be learned, that puzzles would be resolved, that the universe would yield its secrets to patient observation and careful reasoning. They were right to be confident, for the decades that followed would bring discoveries they could scarcely have imagined, building upon the foundations they had laid, extending the human understanding of the cosmos in directions that would have seemed like fantasy in that pivotal year when the expanding universe first became part of humanity's settled knowledge of the world.